speaker of this session is Professor from Tezpur University, and he will be talking on acoustic modes inside white dwarf stars. So his time is 30 minutes, 25 minutes for the presentation, 5 minutes for discussion.
Thank you very much. So first of all, I am extremely thankful to organizers for giving me invitation to present my work here. So accordingly, the title of my talk is Acoustic Modes Inside White Dwarf Stars, and this work has been carried out by myself and my collaborator, Shayanti Dasgupta. She is an assistant professor. So this is about our Tezpur University. Okay, so layout of my presentation is as usual. So this consists of introduction, physical model and analysis, then perturbation analysis, then results, discussions, conclusions, and references. So the main work going to be presented here consists of the published work, these, as well as one more published in JO. Okay, so the density regime where we are interested in can be shown in this phase diagram. So here you can see that this is the region where astrophysical plasma, including our compact astrophysical plasma, as persistent, as existent in compact astrophysical objects like white dwarfs, neutron stars are perceptible. Okay, so everybody knows what plasma is. The plasma is a unique state of matter consisting of a statistically large number of particles, that is typically electron ions, and together with neutrons. Okay, so this is normally it is also called the fourth state of matter, where the temperature is high, and with the input of energy you can see from solid to liquid, liquid to gas, and from gas to plasma we are getting different phases. Out of that, we can say that out of these three, solid, liquid and gas, these are results of phase transitions, but plasma is not a result of phase transition. This is because of what the continuity in your specific heat as well as entropy while moving from gas to plasma state. Okay, and this is a typical picture. So how much energy is needed in order for a gas to get converted into plasma is typically annihilation potential. This is well known as per acoustic viewpoint of both. Okay, and in plasma, one most interesting point is that in case of vacuum, there is no screening of electrostatic potential, but in case of plasma, there is screening of potential. You can see inside plasma, the potential has been screened out with a device screen factor given by e to the power minus r by lambda, where lambda is called device unit length, and we can semi-analytically as well as semi-classically show that inside plasma what happens, the mediators get mass, and this typical mass is dictated by this inequality here, you can see. Okay, but otherwise if it is in vacuum, this mass is zero, that is the mediators are just like massless photons, all the virtual in nature. Okay, fine. And one most important point about plasma is that it is quasi-neutral of a larger scale length with respect to device scale length. So for subcritical scale length, we get quasi-neutral plasma, otherwise it is non-neutral. Okay, and plasma confinement, this is also well known that there are different types of confinement. Out of that, gravitational confinement is more perceptible in the case of astrophysical scenarios, right? Just for example, sun or stars, these are also gravitationally confined plasmas. Okay, and one more important point is that the energy of sun or any star, this is your thermonuclear reaction or thermonuclear conversion of hydrogen to helium, and thereby yielding this amount of energy. But question is that how much matter is converted from helium to hydrogen. Okay, so this is also highlighted. It is and you are typically 10 to the power 11 kg per second, and ultimately what happens after very huge amount of years, that is your millions of years, so it can get its energy, okay, lost, and it happens for sun-like stars, or mainly stars typically having the mass on the order of solar mass, that they are getting the end stage, which is your white dwarfs. So I am my theme is your white dwarfs, so I am focusing in that particularly, but this is just a general scenario, and as you know that a thermonuclear energy reactor going to yield huge amount of energy. This is given by this amount of energy for very long time. This is relatively long time as well, 20 minutes, and this amount of energy. So, and the confinement, what we are considering here, the solar core or white dwarf, etc. This appears in this phase diagram, in this position. Okay. So now the astrophysical realization. So my main work starts now. So yesterday, a previous speakers also talked about star formation processes, which is a multi-stage complex process, right? And this star formation mechanism is triggered with the help of your gravitational instability, which is called Jeans instability. And how it happens, this there is a threshold condition is that in terms of mass, that mass of the dust molecular cloud or the your size, you can say in terms of size as well, it must be greater than Jeans critical mass. Okay, and in terms of size also we can say if it is larger with respect to certain critical scale length, which is called Jeans scale length, only then it will undergo instability. That is, if larger it is unstable, if smaller it is stable. Right? So because of that, what happens? Your global clouds gets fragmented into local clouds, and thereafter they undergo further gravitational condensation. A stage is realized. A stage is coming when the temperature rises too high. Say typically 10 to the power 5 to 10 to the power 11. Okay. 10 to the power 7 also, so very high temperature where thermonuclear burning processes gets immediately triggered, and thereafter you can get the stars. So followed by your pre-stellar cores, protostars, etc. Okay, pre-mentioned stars. So this is how the stars are formed. And question is that if inward gravity exceeds the outward thermal forces, pressure forces, only then you can get a collapse. Okay, so by this gravitational collapse mechanism, your large clouds, global clouds, gets fragmented into local clouds, and thereby finally resulting into the form of your stellar structures. So this is well known, and I am also going to highlight this point as well. And there are different clouds together with their characteristic properties in terms of density and temperature. So these are available from textbooks. Literature is available, and star formation already what I told, and this is taken from internet. One video here also, I don't know whether it is going to work. Oh, it is not working. Anyway, fine. So this is how dust mixture ultimately results in the form of your stars, planets, and our solar system as well. So galactic units are formed out of this dust molecular clouds. So it is not working. I am sorry. And regarding this your planet formation also, one work was carried out by myself and my MSc student, that how planets are formed, and this was a theoretical support to previously reported long-standing gravitational collapse. Okay, gravitational Laplace conjecture about collapse. Okay, and about that foreign stars, the circumstellar dust, they get condensed in the form of your planets. Okay, so your dust rings, so these ultimately getting condensed in the form of your planets. So your planetary structures or planet signals are formed out of this conjecture. Okay, okay, fine. And one more important point is that, so white dwarf compact astrophysical objects, these are basically your quantum. Let me tell you that when the density is high, okay, so interparticle distance is very small. Okay, and vice versa. So if the interparticle distance is very small, a situation comes when the interparticle distance becomes comparable to the de Broglie wavelengths of the associated matter waves. Okay, so if high density situations are encountered, in that case classical Goldman distributions are no more validated. So instead, what we want to apply, we should apply in that case your quantum statistics, that is quantum mechanical approaches are to be applied. So in quantum plasmas, that non-locality effects are to be taken into consideration even in the distribution functions or distribution laws. Okay, so this is the fundamental criteria that for quantum mechanical effects to be dominant, your interparticle distance must be comparable to the de Broglie wavelengths of the associated matter waves of the constitutive particles. Okay, and we have constructed one distribution table between classical and quantum plasma. Out of that, most important points are temperature. That in case of classical, this is high temperature, and the converse is for quantum plasma, right? And then your density, it is in the classical domain, it is low density, but what I told, in the quantum plasma, it is high density. Okay. Apart from that, your Debye or de Broglie sphere. In case of your classical plasma, your this classical plasma, this Debye sphere, it is your superpopulous, that is subcritical, means Debye number must be subcritical. Number of particles in the Debye sphere must be too large, okay, for collective dynamics to be perceptible, but it is irrelevant in the case of quantum plasma, and so forth. Okay. So then again, what I told you, that in case of your classical plasma, the distribution laws of it is your Boltzmann distribution law, and but in case of the quantum plasma, it is your Hermite statistics or distribution laws. Oh, fine. So that occurrence of quantum plasma is everywhere, including your metallic structures, semiconductors, electron gas in metals. Then in the astrophysical scenarios as well, your compact astrophysical objects like your white dwarfs, okay, then your brown dwarfs, okay, dwarf stars, then your neutron stars, then even in black holes. That is your compact astrophysical objects, and even in your Jovian planets, okay. And out of that, which mode is more dominant, or which mode is more relevant in the case of white dwarfs? That is your consisting of your degenerate electrons and lighter nuclei and heavy nuclei. So that is your primarily nucleus acoustic mode. Okay, so here the lighter species, that is quantum electrons, it acts as your screening species, and whereas the lighter heavier species, that is nuclei, this act as your inertial species. As you know, any instability between the two, or extreme instability between the two, excite such type of waves, nucleus acoustic waves. Between the two means electrons and your nuclei. Okay, it is similar to your classical plasma as well. So whatsoever, even in case of gas also, I am going to give one example, because it is a heterogeneous audience. So with the classical oscillator also you can see. Okay, so what you can see in the classical oscillator, you see this is oscillation. Okay, but if the oscillation in the phase space, it occurs in the form of your phase portents, which are your bounded orbits in phase space. Okay, so now these oscillations, if the oscillations are just carrying out but no propagatory characters, that is group velocity, in that case these are just oscillations. But if the oscillations can propagate, it becomes oscillations get converted into waves. That is, waves are your propagatory oscillations. Okay, or conversely, oscillations are non-propagatory waves, like that. So it happens even in your gas dynamics as well. You can see here in case of neutral gas, both the inertial species as well as the screening species are your neutral gaseous constitutive particles, right? Okay. And this is where, because I told you that up to this is your oscillatory part up to omega t, if the argument is up to omega t. But after that, kx is there, that at the cost of this, phase velocity or group velocity features are also assigned. Thereafter, it behaves as a wave. Okay. So these are all basic things available even in textbooks, and you can see in your HR diagram. Okay. So let me first start from nebula. Also, so from nebula, what I told you, that protostars are formed, then Menschevich stars. Out of that, your compact astrophysical objects in the form particularly of white dwarf, neutron star, and black hole are generated. And compactness, whenever you talk about compactness, what is the degree of compactness? That can also be parameterized with the help of density. And you can see just color 1 to 1. So for white dwarf, density typically is on the order of this 10 to the power 12. For your neutron star, density typically 10 to the power 17, and for black hole density 10 to the power 30 SI units typically. Okay, fine. And there are various approaches by which we want to analyze our analysis. So out of that, your fluid dynamical approach, that is your electrodynamical approach, is most suitable. So we are going to apply that one. Okay. So average microscopic fluid with inertial constituted species electrons. Okay. And other kinetic approach, these are complicated. We are avoiding. We are avoiding these only. Okay, fine. And basic approximations are, assumptions are, quantum degenerate plasmas we are considering, Okay, and Bohm potential in the electronic dynamics is considered viscoelastic because of collective correlative effects among the heavier species is also considered, and we are considering the most dominant wave, that is your acoustic wave corresponding to heavy nuclear species only. Okay, and cell gravity is considered because even after being formed, the stars remain cell gravitative, and because of that, everybody knows that for massive, if progenitor stars are massive, then how your neutron stars or black holes are also produced. Okay, fine, and then considered physical model is well closed with the help of gravity electrostatic Poisson formalism. Okay, so with these reservations, we are considering that the relativistically degenerate electrons exist in the inner core, whereas non-relativistically degenerate electrons in the outer mantle. So typical picture is also shown. As you know, for a typical star, and because of the gravity action, gravitational stratification effects as well, you can see that lighter species, they exist in the outer region in the concentric spherical shell model, and the heavier species in the core region, and there is no violation even for your quadro stars configurations. Okay, so this is our typical schematic diagram. So here we can see that the core consists of your heavy nuclei and outer relativistic electrons, whereas the mantle consists of your these nuclei and non-relativistic electrons. Okay, so this is the basic difference, and these are typical parameters for white dwarf stars. Okay, fine. Now question is how to mathematical model. So our system is a closed system. Okay, conservation laws, at least in the lowest order, are assumed to be well validated. So as per that, your first conservation equation, this is your equation of continuity. Okay, this is your electronic density, and this is your radial coordinate, space coordinate, and this is your velocity of electrons with all your general symbols, usual customary notations. This is your momentum equation for electron dynamics. Out of that, quantum mechanics is a non-local theory, and accordingly there is a non-local potential as well. This is called Bohm potential. It is arising because of the overlapping of states. Okay, in the electronic dynamics alone. Okay, and the equation of state is assumed to be polytropic in nature, and so I told you that already relativistic as well as non-relativistic. Two situations in the electronic dynamics are going to be considered. So this is model as per the Chandrasekhar formalism given by your polytropic constant given by this form as well as your polytropic constant given by this. Okay. So here it is given in this form. It is your polytropic constant. This is your polytropic exponent. And if gamma is equal to 1 plus 1 by n is called polytropic index. And these are well known as given in your even fundamental astrophysics. And now, how to model the lighter species, lighter nuclear species? This is accordingly the same equation of continuity with all the usual notations. Then your momentum equation, but here no quantum mechanical features are going to be incorporated, and the equation of state is given by your, this is your isothermal term plus this is your just confinement term. So this is again non-isothermal in nature. This is the equation of state, and accordingly how to model the heavy nuclear species, it is again the same in the same way, but here in addition your collective correlation effects are going to be considered. So that's why viscoelasticity. So this is your viscoelastic elastic term, and this is your viscous term. Okay. So two types of viscosities are considered. One is your shear viscosity, other one is your bulk viscosity, opposing your flow as well as radial expansion respectively. Okay. And the equation of state is the same. Now these are standardized with the help of scale-free normalization scheme, and these are various normalization factors, and we are interested in studying the stability behaviors with respect to particularly these parameters. So that's why I have highlighted, and one more here. Okay, so rotational effects are also considered. Okay, fine. So what we find after normalization, the respective equations look like this with all the usual formalisms in spherical coordinates. Okay, and after this we want to apply sorry, spherical wave analysis, but spherical wave analysis under spherical symmetry. That's why your angular parts, your polar parts, azimuthal parts in the form of spherical harmonics are no more going to be considered, but instead we can simplify this with the help of your plane wave part this and modulated by your 1 by r dependency, which takes into consideration the geometrical curvature effects. and equilibrium is hydrostatic homogeneous according to the equilibrium values. And after substitution of these, we get the linearized equations of the above closed set of equations, and respective forms are given as follows. Okay, so your quantitative equation, momentum equations, and Poisson, gravity electrostatic Poisson equations. So Poisson equations are given for electric field, electric potential perturbation, as well as your gravitational perturbation are given this way. Okay, now we do the method, apply the method of decoupling. After that, all these equations get reduced in the modified Fourier space, omega k and giant, and it looks like this complicated dispersion relation of septic in degree. Now, these equations can be further solved numerically, okay, and these are reduced form of the same equation, and
the
results.
approximation you used, is that?
Sorry?
The approximation you used?
Yeah, low frequency approximation, very low frequency approximation. That's why the above complicated equation gets reduced into a simplified form, okay, and these are various coefficients. Okay, so these are results we got. So growth rate, you know, so whenever we are interested in finding the stability of any given dynamical system, we first start out the system over the equilibrium, right? So here omega r, that is your equilibrium frequency, over that perturbation appears in the form of your omega I, and it will be growth rate, okay? Okay, so first we plot this growth rate, and it appears of this form that with respect to mu. So if mu increases, we see the growth rate decreases, right? And it happens in both your non-relativistic as well as ultra-relativistic regime in a combined form given here. So here from we conclude that mu acts as a stabilizing agent, and physically it happens because that as mu increases, already mu has been shown where it is already mu has been shown as the ratio, okay, modified ratio of equilibrium density of heavy nuclei and light nuclei modulated by this Z, and Z is your just charge number ratio, right? So if heavy nuclei are increasing, then what happens? Your gravitational effects are also increasing, and that prevents your acoustic behaviors, and because of that only it physically happens, okay? So we are finding that mu acts as a stabilizing agent. Okay, and similarly we investigate for other parameters as well, and similarly we find that beta acts as destabilizing agent in the same way. Okay, the physics being the same. Then at the same time we are also finding that your Coriolis effect, that is your rotational effect, that also acts as destabilizing agent. So this is just one typical example I have shown, but rest are I am not going in detail, that other things are also in different configurations also we have found, and this entire picture is now confirmed with respect to your color spectral profiles. Okay, so we are finding that yes, of course these are correct, and these are various conclusions which we can draw out of this your simple analysis. So from this analysis we have just developed a theoretical very semi-analytic model to investigate the nucleus acoustic waves or acoustic waves in dwarf stars, white dwarf form, okay, and various realistic agencies were also incorporated statistically, and various stabilizing, destabilizing agencies were also analyzed and characterized. Then at the same time, we also compared as the reliability test with respect to your previously reported results, and we found that regarding the experimental detection, observational aspects, these are the missions which are promising in this direction, but of course not exactly determined up to that level, and that applying the same strategy, same mathematical strategy, we have also found out a GNO instability mode in your crust of neutron stars, where neutron is heavy nuclei and your superfluid neutrons and quantum mechanical electrons are considered. This is also similar one, that acoustic mode in your compact astrophysical objects in the form of neutron stars, which has been published in scientific reports. Then at the same time, we have also found out your low frequency modes in the course of your white dwarf stars, okay, which has very recently published. Then at the same time, another core we have studied for your in cylindrical geometries. It is also in scientific reports. Then one more, the latest result that has it got published in Roman Journal of Physics very recently. Again, similar features, okay? And here I would like to show whether it is working. No. There's a video that from compact astrophysical objects and in your interstellar space from dense plasma as well on the astrophysical scenarios. So there is a video that they have detected various sounds and various acoustic signals from NASA Voyager 1, and these are also audible. You can also see here, but I am very sorry that it is not working here. No videos are working here. Okay, so here from also it is a reliability test that whatsoever we have been doing, although purely from theoretical point of view, but ultimately we are getting matching or reliably supported by other observational effects as well, observational missions as well. Okay, okay. So this video, oh yes, it's working. Okay, fine. So here you can also, if you switch is on, can you switch on? Then you can also see, just listen to the music, plasma music. Okay. Anyway, so these type of waves are also detected and also reported by various missions. Okay. So we are putting one theoretical support to the already existing reports. Okay. 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 So before I end, I want to end this with this famous quotation with Albert Einstein. So once we accept our limits, we can go beyond them, by Albert Einstein. Okay. So thank you very much for your time.
Our speaker, I request Professor Ajay Misra to come and make his speech. Good.
Good morning. I am Bhaskar Jyoti Varman from Assam University, Silchar, and today my topic is the effect of turbulence and density on magnetic field geometry of dark clouds. Here is the abstract. So we collected 22 isolated dark clouds from which we study the effect of turbulence on magnetic field alignment and the effect of density on their turbulence. So let's check the briefly what is molecular cloud. So basically molecular cloud is where the stars are formed. It contains hydrogen, helium, 90% hydrogen and 10% helium, and they are very cold. The temperature is 10 to 20 Kelvin. So their classification: giant molecular cloud, high latitude diffuse molecular cloud, and small molecular cloud. Here is the three example of that and their properties. So there is a famous Jeans criteria. If the molecular cloud accumulated that amount of mass, then it can form photostar. That is the first beginning step of the star formation. So here is the Jeans mass. So our study is magnetic field. So what is the importance of magnetic field on this Jeans criteria? So in 1976, Mochovius and Spitzer given relation with this magnetic field with Jeans mass. So here is the criteria, and from that we can find the mass to flux ratio from by virtue. If it is less than 1, then the magnetic field will prevent the collapse. But if it is greater than 1, then magnetic field cannot prevent for collapse. So from polarization one can get the magnetic field vectors. Can study the magnetic field of molecular cloud. Here is some example of magnetic field lines of molecular cloud. Let us take an example of CV17, the second one. We can see that the white lines are the direction of magnetic field lines, that is the polarization vector, and the above dotted white line is the line of galactic magnetic field. So from that we can see that the white lines, that is the local magnetic field. The local magnetic field is aligned with the galactic magnetic field, that is parallel. But we can see that CV88, the lines are not parallel with the galactic magnetic field. So with this motivation, in 2022, Chaudhary et al. Find a relation with the position. So they found that at low longitude range 0 to 100, they found that the offset range is so high. The alignment of galactic magnetic field and local magnetic field is so high, but at the region, at anti-galactic center region, the offset is very low. That is, local magnetic field is parallel to the galactic magnetic field. This signifies that the galactic magnetic field can affect the local magnetic field. So, they find this relation by position, that is galactic longitude. So there is no physical effect. So we try to understand there is any physical effect of on this offset. With this motivation, we collected some data of turbulence. So turbulence is basically the chaotic motion on this molecular cloud. The turbulence velocity we collected, that is the CO emitter lines, that is full with half maximum. We use that turbulence velocity. As molecular cloud 98% hydrogen helium, but hydrogen helium cannot emit at very low temperature. So the second most found element is CO. So we use that data. So we collected the archival data of the turbulence velocity we listed, and we also listed the offset of 22 molecular cloud, and we plotted with turbulence and offset. Here we can see that at high turbulence, if we can clearly check if the turbulence is more than 4 km per second, the molecular cloud exhibit high offset, and we know the offset is basically the difference between the local magnetic field and galactic magnetic field. So here we can clearly see that the offset is very much high, and at low turbulence velocity, the clouds are parallel to the galactic magnetic field. We fitted this point with second order polynomial, and we find a very good fit, that is the coefficient of determination is 0.8. And we also study the effect of density on this turbulence. Here we can see that when the density is very much low, the molecular cloud is very much turbulent. Here for CV54 130 and CV3 and 34, it is very much high turbulence, and when the density is high, the turbulence is low. So here is the results and reference, and thank you.
Okay, good morning everyone. So in this presentation I am going to talk about using Big Bang nucleosynthesis as a probe to constrain FR gravity scalars and primordial black holes. So let's start with GR. This is the most experimentally tested theory over the last 100 years, and it has given some remarkable results. So experimental results, and this is a well-known Einstein-Hilbert action, and from this we can derive this field equation. Well, left hand side is geometry and right hand side is basically the matter energy tensor. So now when we go to astrophysical scales, so we can take the right hand side to be 0 as a more simplified scenario, for example like black holes and in the solar system. But if we go to cosmological scale, we cannot do the same thing because our universe is not empty. It contains many large scale structures, galaxies and all these things. So in the standard model of cosmology, what we do, we actually consider a spherically symmetric FLRW metric, and we let the equation of generality evolve, and we get something known as this Friedman model. So it says that the rate of expansion of this universe is basically dependent upon different entities present in our universe. So this equation is very important for our work because we are going to modify this in the FR scenario when we will study that. So now, if we consider general relativity to be the governing theory of gravity in cosmological scale, there are some fundamental problems. So like there is an occurrence of cosmological singularity at the beginning of our universe. Second problem is that to explain the stability of large scale structure, we need an exotic matter component called the dark matter. And the third problem is to account for the observed acceleration of this universe, we need another repulsive exotic component known as dark energy. So now, obviously, occurrence of cosmological singularity automatically means the breakdown of ZR, and there has not been any kind of confirmed experimental candidate for dark matter and dark energy has been found. So now, what we have been doing, because ZR has not been tested extensively in cosmological scale, so we are basically dealing with an unknown theory. We have extrapolated to a large scale, and it gives us some exotic components, and we are doing science with that. It is something like very risky business. So now in the language of James people, so ZR in the cosmological scale may be spectacular extrapolation. So that's why we have been searching for alternatives. Maybe dark matter and dark energy are not exotic substances. They might be large scale modification of general relativity itself. So now, one way to modify the theory of gravity is obviously to modify the action. So this was the first one in 1961 given by Carl Branch and Robert Dicke, where they introduced a universally coupled scalar field. But in our work, we have considered a geometric modification to the general relativity, a general class of theories known as the FR gravity, where this scalar is replaced by a more general function of R, so that is FR. And now, the first prototype was given in 1980 by Starobinsky. So, and it has successfully solved the problem of inflation, and it has also been able to remove the singularity, which was a problem in general relativity. And more interestingly, it actually was able to explain or give a black hole solution. Let's see how. So, if we consider this is the field equation of FR in metric theory. We take the trace of it, then taking the vacuum and a constant curvature background. Here we arrive at this equation, and this is essentially a Schwarzschild-Digital black hole solution. So now we have a black hole in FR. So in FR gravity, if we take into account the quantum corrections near the black hole horizon, curvature correction to quantum vacuum fluctuation, we basically get some extra scalar degrees of freedom, known as the scalarons, and they are mediated by something called the scalar field amplitude. So this is the expression. So like if we consider a linear perturbation around that scalar field, so we can actually derive a relationship between the black hole mass and the associated scalaron mass. So this is a very important relation in our work, because to constrain the black hole mass, we are going to use this one. So it has an inverse kind of relationship. So now let's come to the primordial black holes, because this is primary in our work. So the usually considered range is 10 to the power minus 38 to 10 to the power 6. The lower limit comes from the Hawking evaporation time. Anything lower than this would have evaporated by the present time, as you can see in this graph. So for this mass range, the time of evaporation is with respect to the age of the universe is quite big. So those black holes are likely to be existed still so far. And for the upper bound that we have taken, it basically comes from the formation time of these black holes. So basically, the formation time, as you can see, so it is much less than 1 second, because the Big Bang nucleosynthesis is 1 second, so it is much more than, it is lower than 1 second. That means it has, these primordial black holes have formed much before Big Bang nucleosynthesis, and that is the reason why we can consider these primordial black holes to be candidate of non-baryonic dark matter, because baryonic dark matter has not even formed yet when these black holes are here. So now, correspondingly from that relation, inverse relation, we can actually obtain the scalaron mass range corresponding to this black hole mass range. And because we are going to see what kind of effects we can get because of FR gravity in the Big Bang nucleosynthesis, so this is actually given by something called the unspinning, as Dr. Rati has already yesterday talked about this one. But still I will say, if the dimensionless gravitational potential, this one, it is greater than the scalaron field amplitude, so we won't get any kind of effect. So gravity will dominate. But if this scalaron field amplitude is greater than gravitational potential, Gm by c square r, so those scalar fields are going to escape, and this is going to affect the surrounding environments. And for this range of black hole masses, so we can see that this ratio is always greater than 1. So this can affect the different kind of cosmological events, for example, like Big Bang nucleosynthesis at that point in time. So, and this plot we say as LPDK sci-fi plot in the name of four authors, Lalendra Atik, Paul, Taludra and Kalita, because we have been actively working on this scalaron field, and in different kind of environments we have used this plot, so that's why this name. And now let's go to our scenario or probe Big Bang nucleosynthesis. It is basically the synthesis of light elements in our universe. So now the synthesis of light elements in our universe is a competition between two different things. First one is the interaction rate among different particle species that has been going on in the early universe, and the expansion rate of our universe. When the temperature was quite high, so there was an equilibrium maintained among different species, nuclear species. But when this temperature came down to nearly about 3 into 10 to the 9 Kelvin, this nuclear reaction and the expansion rate, they become equal, and we call it the freeze-out epoch. And the neutron by proton ratio, the density, so it becomes fixed, and from that neutron by proton ratio we have to derive everything, all the elements that we get in our universe. So because now the equilibrium is broken, the neutrons are also beta decaying. So within that very small window, 1 to 1000 seconds, we have to synthesize all the elements. So that's why we don't get very heavy elements in the early universe. So to constrain the thing, the mechanism we have used is that if we, I have showed you that Friedman model, if we introduce some gravity sector component, so it is obviously going to increase the expansion rate of our universe. So in this scenario, we have used the scalar degree of freedom, the extra degree of freedom into the Friedman equation, and as we can see that it obviously this is going to increase the expansion rate of our universe as compared to the ZR scenario, and obviously now the freeze out will occur much earlier. So this shift in freeze out is going to cause shift in the elemental abundance, the primordial abundances, but any kind of arbitrary modification to abundances is not allowed because we have very accurate measurement of the abundances in our universe. So we can use those observation to constrain the masses of this scalaron. So this is basically the formalism. So this is basically nuclear reaction rate lambda. It depends upon freeze out. So considering the freeze out epoch where expansion rate and the nuclear reaction rate are equal, so shift in freeze out is obtained as a function of scalaron mass, and similarly the helium abundance. So now we have observed values. So using the observed upper bound on the elemental abundance and freeze out shift, we can basically give a constraint on the scalaron mass range, because as you know, this is dependent upon scalaron mass. So now this is the constraint scalaron mass, and I have showed you that relation between scalaron mass and black hole mass, and from that we can get a constrained black hole mass range, that is from 10 to the minus 14 to 10 to the 6 solar masses. So here is another one thing. So the parameterized post-Newtonian parameter gamma, so it has a relation with the scalaron mass. So now what we can do here is that, so if we take the scale of our solar system where 0.004 is the solar radius up to the radius of hypothetical planet 9, people are talking about 800 AU, and we have constraint from Cassini mission on the parameter gamma, so we can actually derive the range of scalarons that has been allowed in our solar system, and as you can see, this is accommodated here in our graph. So this is the whole allowed range of scalarons and black hole mass that is shown in our graph. So now the last portion. Yeah. Okay, sorry. So now this thing, the results. So we have also tried to see what this how this FR scalars can affect the surrounding environment. So we have calculated the neutron abundance and deuterium abundance in the early universe in presence of these scalarons. So as you can see, this red line is the general relativity, and we have considered the possibility of relativistic and non-relativistic scalar using the yellow and green line, and these are almost, the deviation is minimal. So that means we can say that basically FR scalarons are mimicking something like ZR, and the expansion is like kind of ZR expansion history, so not deviating too much. Similarly, we have calculated the combined deuterium and helium abundance in the early universe in case of both relativistic and non-relativistic scalarons, and it is also matching with the pre-solar abundance, within the error bar. So the conclusion is that now BBN constraint give us the scalar and black hole mass range as 10 to the minus 14 to 6 solar masses. So now the interesting thing is that this primordial black hole mass range is purely derived from scalar gravity, and it is now compatible with the non-baryonic dark matter that has been previously explored in the previous literature. So that's a nice thing. And the thing that the scalar mass range that we have shown, 10 to the power 4 to minus 16 eV, it can also give rise to axion-like dark matter candidates. So that is a very important findings from us, and obviously the determination of abundance of the Riemann neutron fraction is showing is here like expansion history. So we can finally conclude something like that, that this FR scalar gravity can be a serious alternative to general relativity in the early universe, because all the evidences are giving hint towards that. So this was basic communication with Jacob. So thank you for.
Good morning, everyone. I'm Momi from Tezpur University. I'm happy to be here, and I want to thank the organizer for giving me the opportunity to present my recent research findings here. And I'll be talking about the impact of convection and metallicity on the instability strip edges of classical CFIs. Yesterday's Snigdha has given a very nice explanation about what is CFIs and how to use MESA RSP. So I'll not go much details into this. Okay, CFIs are intermediate mass for helium-burning stars with partition period ranging from 1 to 200 days, and their population 1 star. And these animations shows the how the brightness of CFIs is changing with time, and this is a CFIs with period 31.4 days. And this is Henry the Legit, one of my inspiration. And she for the first time discovered that the luminosity of CFIs is strongly correlated to their period. And this relation is known as period luminosity, and in short, PL relation, or we also know it as Leavitt law. And it's her discovery which has made CFIs an essential step in determining the size and age of the universe. And okay, this is one of the most important diagram in stellar astrophysics, and this is the Hertzsprung-Russell diagram for pulsating stars. And these dashed lines here, dashed lines here indicates the instability strip edge for classical pulsators, and CFIs lie in this within this region with other classical pulsators, and this region is known as classical CFIs instability strip, and this region is home to all classical pulsators. Hence, the PL relation obeyed by them is strongly coupled with the interceptor slope of this instability strip edge, and the strip edge towards the higher temperature is known as blue edge, and towards the lower temperature is known as red edge. And here we will be looking at the metallicity effect and the turbulent convection parameter effect on the strip edge of this classical CFIs. Okay, why we are interested in the metallicity effect? Because classical CFIs are vital ground for cosmic distance ladder, and hence also crucial for determining the Hubble constant. However, the discrepancy between in the value of H naught measured from cosmic microwave background and the local measurement, which is based on this cosmic distance ladder, is still not resolved. And recently it has been found that incorporating the metallicity term in the peer relation has improved the distance ladder. However, there is again one contrast between this metallicity coefficient. When we incorporate this metallicity coefficient in the peer relation, it has been found that the coefficient of metallicity from observation point of view is negative, while from theoretical models it is found to be positive, except one study who has found it is negative. And this might be due to our poor understanding of these turbulent convection parameters. So what is convection? This is a very good example of transfer of heat by convection, because the water from the bottom, when it gets heated up, it gets less denser, so it rises up, and the cool water from the above, as it is highly dense, so it will come, it will seem to replace the previous hot water. So this cycle continues, and this is a very simple picture of convection. But when we move to stars, okay, this shows the solar surface convection, And when we move to stars, because of its large scale structure as well as low viscosity, convection become a very complicated, and and we know that convection is a three-dimensional, turbulent, nonlinear, time-dependent process. So it becomes really computationally expensive. And again, we are trying to implement this three-dimensional process in one-dimensional stellar code. So to incorporate this one-dimensional stellar code, we have to assume lots of approximation, and this has been done by assuming this has been achieved using multiple user-defined parameters. These parameters are known as turbulent convection parameters. And for generating the theoretical models here, I will be using I have used MESA-RSP, and in MESA-RSP we have such 8 such parameters. And SETE is the simplest one, which has not incorporated the turbulent pressure, turbulent flux, and radiative cooling. And SETE is the most complex one because it includes all the 8 parameters. Okay, this is the color magnitude diagram from the observed data. We have used oval for archival for this, and here the first panel is for large Magellanic cloud, and the second panel is for small Magellanic cloud. And here the black points in the we have discarded the black points because of high uncertainty in their extinction. And this is the theoretical model grid, input parameter grid we have constructed by going through various literatures, and it spans the mass, luminosity, and temperature, effective temperature parameter space typical to classical sphere. And for metallicity, we have considered this metallicity typical to SMC, LMC, and Milky Way. And these are the models we have obtained from MESA-RSP. This is also the color magnitude diagram. It includes both stable and unstable models. The yellow points are the unstable models, and blue are the stable models. When we talk about unstable models, so it means that it will pulsate and we will find them inside the instability state. However, to find the edge from this picture is quite challenging. So for this purpose, we have used the machine learning technique, and this is our result. Here the blue and red is represent the blue and red line represent the blue and red instability edge, and the orange points are the theoretical models, and the purple points are the observed models. And this is for LMC and this is for SMC. And when
where do you take the data?
So for a comparison with observations, so that our predicted edges are consistent with observations.
Means you have taken data. And
Oh, yeah. It's archival data. Oval.
Archival data means from which source?
Oval. Okay. Here I have plotted all the observed data and our predicted ISHs, instability strip edges, and we can see that when you consider only set and set B, it can cover the hotter observed stars quite well, while set C and set D is needed to cover the models, cover the observed star near the red edge. And we have seen that more than 90% of the observed stars are within our predicted edge. However, at this moment we are not in a state to make a statement which set is more suitable, and we are looking forward to find only single parameter set which will be suitable for classical sphere. And we have also seen that with the complexity of the turbulent convection parameter set, the edges are becoming redder. And this might be due to these two parameters, turbulent pressure and turbulent flux. And it seems that these two parameters are making and damping the pulsation in the models with high temperature, while exciting the pulsation with models with lower temperature. And we have also looked at the metallicity effect, and here we have found that with increasing metal fraction, the edges are becoming redder. Edges are becoming redder. This might be due to the fact that when the actually it is expected that when metal fraction is increasing, the edges shifted towards radar direction. When helium fraction is increasing, the edges are expected to shift bluer direction. But as we have increased the metal fraction here, subsequently helium fraction is also increasing. So we have seen a very mild effect here, not a very significant effect. And one more interesting findings of our work is that these flared models, we have not seen any such observed stars in the observed color magnitude diagram. However, this can be seen from the theoretical data. So we are hopeful to use this model to optimize the turbulent convection parameter set to find one single parameter set suitable for classical series. And this is my summary. And before ending this talk, I would like to acknowledge the contribution of my collaborators. And I would also like to acknowledge Tezpur University and IUCAA for providing me the facility, and CSR for the research time. Thank you.
So, very good morning to everyone. I'm Arvind from Tezpur University. So, the title for today's talk is Study of Energy-Dependent Temporal Nature of MAXI J1803-298. So, my collaborators are Professor Rajiv Mishra from IUCAA Pune and Dr. Akaskar from IUCAA Pune. So, the results which I will be showing here in this talk are preliminary results of our ongoing work. So I will start with a very brief introduction to X-ray binaries. So X-ray binaries are a binary system consisting of a compact object and a normal star. So in which this compact object accretes a material from its companion. So in the process of accretion, it prominently emits an X-ray. So they are known as X-ray binaries. So basically, this depending on the compact object, they are further categorized as a black hole X-ray binaries or a neutron star X-ray binaries. So since this source MAXI J1803 is a black hole X-ray binary, here I will briefly discuss about black hole X-ray binary. Mostly black holes.
Where it is located?
Yeah.
This one. What about LB?
Yeah.
Of the source you have considered?
Yeah.
The source which we have considered, what is RNA or what is the galactic location, radiation location?
So I forgot, but it was maybe near to this globular cluster, but I forgot. I'm not sure. Okay, so now talking about black hole X-ray binaries. So basically, these black hole X-ray binaries are transient in nature. So mostly they remain in quiescent states. So once they undergo their outburst phase, it travels to a different spectral states, starting from a hard intermediate to a hard state to an intermediate state, then to a soft state, then it goes back to a quiescent state. So one can easily see from the HID that in which state a system is. Okay, so it is seen in most of these black hole systems that they follow some kind of Q track, as seen in this in the right side of this figure 2. So in order to understand the hard state and soft state, so there is a figure at the left hand side. So in hard state, what exactly happens or what we believe is, on considering the scenario of a truncated disk. So these truncated disks are adjoined to this corona, which is in between this ISCO of a black hole and the inner disk of inner radius of this truncated disk. So the soft photon from this disk will be inversely protonized in this corona. As a result, the hard photon will be produced. So the hard exchange will be observed. So it will be a hard state. Similarly, once this truncated disk moves closer towards this ISCO, so then both the spectra observed during that phase will be a combination of hard and soft photons. That time we will see a short-lived intermediate state. So once this truncated disk reaches ISCO, then we will see the soft photons. Then as a result, system will move towards this soft state. So now talking about this MAXI, the source. So it is one of the newly discovered black hole candidate detected on May 1st, 2021. So during its outburst, many satellites has observed it, says Jana et al. 2022 and Chand et al. 2022 studied this source using the associate observation, and they observed very nice type C QPO. And in Chand et al. They confirmed that the compact object is a curved black hole with a spin of 0.7 and a mass of about 8 to 16 solar mass. Similarly, Finn et al. In 2022 estimated its spin to be 0.991 with an inclination of 70 degree, and they have performed this reflection modeling of a simultaneous Neisser and Nusser data. Similarly, Zhu et al. In 2023 studied the source evolution through different spectral states using this HMXT and Neisser data through a timing analysis. So this is a maxi long-term line curve during its outburst. So here these marked lines are the observation done by the associate and Neisser in the month of May. So starting from the initial days of a month till the 31st of May. So this red line represents the Neisser observation, which is around 27 observation, and this black dotted line represents this associate observation. Okay. So the primary motive of this work is to compute this energy dependent time lag and RMS of a QPO at different frequencies and model it using a comprehensive technique developed by Gerg et al. In order to find the origin of a QPO. So here I will be discussing about this model. So in black hole system, the observation of QPO is quite common, but the origin of this QPO is still in a debate. Though there are many theoretical models which has tried to explain the origin of a QPO, but there is no such concrete model which has been validated. So in order to explain this origin of QPO, there is also an alternative approach, that is to identify through a radiative process. So it is seen in most of these black hole systems that this QPO frequency are correlated with the spectral parameter. So it is important to develop such technique that can test a model prediction of a timing property based on this broad band spectral analysis or information. So with this point, this Gerg et al. 2022 described a comprehensive technique to model this timing property based on the spectral information of this source. So these temporal properties which can be obtained by a numerical differentiating model spectral component and using them to estimate a variation of spectral parameter that can explain the timing result. To do so, the spectral component will be chosen in such a way that they are non-degenerate and not necessarily a physical relevant one, such that those components will be transformed to the physical quantities, and with the variation of that physical quantities we can predict about the timing properties. So basically in the time average spectra of a black hole binaries are often dominated by two spectral components. First is multicolor truncated disk and thermal plasma, which comprise a photon from the disk. So in XPEC there is a function called dixability, which helps in understanding this multicolor truncated disk, and there is NTHCOM or THCOM, which helps in understanding this thermal plasma, which comprise the photon from the disk. So if we use these models to model the our spectral analysis, then on transforming those parameters of this model into a physical parameter and using those physical parameters to model this energy dependent and time lag RMS, we can find the model parameter which are responsible for the source variability. Basically, we focus on these four possible physical parameters whose variation can lead to the observational this energy dependent variabilities, such as this inner disk temperature, coronal heating rate, fractional scattering, optical depth, and normalization of a disk. So, preliminary detail. So, during the month of May, Astrosat has observed this source twice. On checking the light curve, we saw that those observations were continuous. So, we are considering it as a continuous one observation, and we segmented it into a 14 segment on the basis of consecutive. On the basis of frequency we observe in a consecutive segment. For example, if segment 1 and segment 2 has a similar frequency with an error bar, then we are considering it as one segment. In that way, we have segmented up to 14 segments. And we did PDS fitting for each segment. We saw very nice QPO, and we checked the variability of QPO with the segment, and there is a variation in the QPO frequency with the segment. Then we perform a spectral analysis for each segment using a very simple model like constant T-Babs, TH-Cup, and DIX-BB, and the spectral component of from this model were transformed to a physical quantities. Then those quantities were used to model this RMS and time lag. Okay. Then the information what we gathered here from this table is that the heating rate is leading the change here. So through our analysis, we can say that the variation in the QPO frequency initially started from the heating rate, then in the change in the inner disk temperature. So here is also nicer. We also perform here in nicer also we perform this PDS fitting. We saw QPO. We did this same QPO versus MGD. There was a variation. Then we performed this spectral analysis using the same model which we have used for AstroSet. Then we did the same thing, that we transformed the spectral component to a physical quantities. Then we used the quantities to find to model the RMS and time lag. And with the result, what we observed was very consistent with this AstroSet result.
2 minutes.
Yeah. So the conclusion. So till now, our conclusion. So we conclude that this initial two observation of NICER were in a hard state with a photon index less than 2, and as this system transitioned towards this intermediate state, we saw the increase in the photon index with the range of 2 to 2.7. So the presence of type C QPO in AstroSet observation and with the support of a photon index, we concluded that the system was in hard state. But in our 14th segment, we observed that the Q factor of the QPO was very less than the other QPOs. So we believe that during that exposure time, the system was transitioning towards this soft intermediate state. So in NICER observation, there was this type B QPO, and the photon index were also supporting this system to be in a soft intermediate state. So after this 59361 MJD, the system, we believe that system may have transitioned towards a soft state, as we did not observe any QPO and the photon index value were also high. So till now we believe that from our preliminary result that the variability is due to the variation in inner disk temperature and the coronal heating rate. So these are the references. Thank you.
Hello everyone, still good morning to all of you. I am thankful to Mizoram University, particularly the organizing team, for inviting me to share some of my experience with the field of gravitation in this platform. I will be talking on what is the current status of general relativity, which is foundation for relativistic astrophysics and cosmology as a whole, as far as recent observations are concerned. And I have one extension, organizer may note it. Some cases near the galactic center black hole, I will discuss whether we have been able to test GR near the black hole environment. If yes, then what are the implications? Let me start with Sir William Herschel, the first thinker to extrapolate the law of gravitation to stellar systems. And in his book, in 1785 book on the construction of the heavens, he first put forward the idea that gravitation reaches to the stellar systems. Of course, he was referring to Newtonian gravitation. We have a remarkable prediction on the basis of Isaac Newton's theory of gravitation, the discovery of Neptune, and just by using Newton's theory of gravity, a serious anomaly in the orbit of Uranus was resolved, and the result is existence of this beautiful planet called Neptune. But in science, it is very important to find out true anomalies. Finding anomalies in science is a lesson. Black body radiation is an example. Similarly, Einstein's gravity to explain the anomaly in the Mercury's orbit is another example. Now, the problem that we have the general relativity, which is supposed to be the established paradigm for gravitation, has not yet been able to address serious anomalies in the field of cosmology without addressing unknown physics, without incorporating unknown physics. And the unknown physics is, of course, dark matter and dark energy. We have to incorporate the existence of exotic matter and exotic energy field to explain the dark universe. These exotic matter fields may be modification in the matter sector of Einstein's field equation, or maybe it is a completely new gravitational physics. If it is a completely new gravitational physics, the theory is in trouble. Now there are problems with general relativity, well-known problems, and there are some new problems that we have realized. The first problem is that it is too successful. Being successful in science is sometimes not very good. And this is the reason that we have a courageous extrapolation of the theory to cosmological scale. Of course, we have space-time singularities, both in classical black holes as well as in the initial singularity. That problem is not yet resolved because GR is incompatible with quantum theory. Cosmology has dark matter and dark energy. We doubt that it is very difficult to explain the observed features of the universe. But the physics of dark matter and dark energy is not yet known. The serious problem is that are black holes of GR, or they are black holes of alternative theory of gravity? This is an unsettled issue. These are some serious problems we are experiencing in GR. If there are problems, then test it. Test is important. Why we need test of the theory? I always refer to Karl Popper, a German philosopher who said a theory should be falsifiable. So general relativity has not yet been falsified. Then this is the issue of concern. Till now we have tested very accurately the weak field limit of GR, but what about weak field limit of other consistent alternatives to general relativity? This is the reason we are continuously testing the theory. If we talk about testing the theory, we have to remember Sir Arthur Eddington, who initiated the empirical foundation of general relativity and any geometric theory of gravitation by observing the deflection of light in the famous 1919 solar eclipse experiment. And that experiment was the foundation for theory of gravity, of course, and gravitational lensing, including micro lensing, strong lensing, and weak lensing, which is important for studies of exoplanets, important for studies of large-scale structure and the dark energy physics. Now, in order to have astronomical test of general relativity or any other theory of gravity, Norbert, Will, and Kip Thorne, they devised a formalism known as parametrized post-Newtonian formalism. In this formalism, we parameterize the weak field limit of any theory of gravity by two parameters. One is called gamma and another is called beta. Gamma measures how space is curved and beta measures how nonlinear gravity is. If gamma and beta they are both 1, you will get back distorsive metric. If they are not equal to 1, the weak field limit of the theory will be different from GR. So all astronomical tests including light deflection, perihelion shift, Shapiro time delay, etc. finally have constrained the value of gamma and beta in our solar system. And what we have found from 1920 up to 2010, or maybe more than 2010, by 2022, the gamma parameter has been accurately found to be very close to 1. If the plot shows 1 plus gamma by 2, different experiments, Shapiro time delay, deflection of light, perihelion shift, particularly Voyager spaceship and Cassini spaceship, it was measuring the Shapiro time delay of light rays in the solar system because of the presence of massive object like Jupiter. And if we see these error bars, this gamma is 1 up to the factor of 10 to the power minus 5 if we look into Cassini data. And that is, I think, realization of something known as perfection in science, that in solar system we respect GR too much. This is the summary of the testing, the theory of general relativity in the solar system. But there are tests beyond the solar system because of technology. Binary pulsars have been used because they revolve around each other and the orbit decays due to emission of ZW. And the exact rate of decay has been tested and found to be matched with GR prediction. I will be talking today about monitoring compact stellar orbits near the supermassive black hole sitting at the heart of our galaxy. This is a strong probe for testing gravitation in a gravitational potential which is 10,000 times larger than the potential that we experience in case of the Sun. So this is a novel probe for testing gravitation. There are tests in the galactic scale, in the scale of large scale structure, as well as by using the cosmological abundances of the light elements. I will not discuss all of them, particularly I will tell about the galactic scale test. When we talk about galactic scale test, we usually take the weak field limit of galaxies. But galaxies are building blocks for cosmology, so when we take weak field limit in galactic scale, we get perturbed FLRW metric. A is the scale factor, and phi and psi, they are known as Burdeen potentials. If they are same, the theory is usual FLRW. If they are not same, we get a process called gravitational slip. So ratio of psi and phi, they determine a quantity called PPN parameter in cosmology, or we call it as a slip parameter. And strong gravitational lensing particularly has measured the gamma parameter in the scale of galaxies. What is strong lensing? If you have one galaxy and another galaxy aligned perfectly in your line of sight, the light will be bent and possibly you will get multiple arcs. That process is called strong lensing. Sometimes you will get multiple point images. So strong lensing directly probes how gravitational field is behaving in the foreground object. So you can test the gamma parameter out of that. And see the numbers, 2018, then 2022 people have measured, and general relativity has been found to be okay with this scale. In large scale structure, we test the theory by looking into observed clustering rate of the galaxies. See, when the structure forms after the Big Bang, they are sensitive to the background expansion, and background expansion can be altered if the theory is not GR or the background is not FLRW. Therefore, the rate of formation of structures is sensitive to which theory of gravity you are referring to. And because of this, we have a probe called large scale structure probe. GR predicts that the structure growth, which is a dimensionless function called Fz, it's a function of cosmic epoch, redshift. It is matter density parameter to the power beta, and GR predicts beta as 0.55. And observations concerning clustering of galaxies, people reported, which is satisfactory with general relativity. So in LSS test, in one of the LSS tests, we also found that GR is working well. But keep your mind open. There are some large-scale structure tests where the theory has been found to be shaky. Gravitational redshift is a foundational prediction of Einstein's equivalence principle, or the very foundation of GR, that whenever you have massive object and light propagates out of the gravitational field, the light gets redshifted. It's called gravitational redshift. Alternatively, blue shift also occurs. If you come from weak field to strong field, gravitational blue shift will occur. SDSS data release 7 in 2009, and brightest cluster galaxies have been used to measure the redshift for the first time in these scales. And if we see the three graphs, the gravitational blue shift of the light coming from the galaxies in clusters of galaxies have been measured with respect to scale that you can see in the x-axis. From the graph, we see that tensor vector scalar theory has been completely ruled out. Now, what is TVS? Tensor vector scalar theory is a relativistic generalization of modified Newtonian dynamics that people use to explain the flat rotation curve of galaxies. That has been completely ruled out. But general relativity and FR gravitation theory, they are both eligible to explain the redshift. That is the beauty of this particular test. Of course, this is the only redshift test in large scale structure. People are still working whether we can have some more tests to rule out any one of them. So this is how we realized that it is possible to test the theory and its alternatives in different scales. Now, test near the galactic center black hole. Since the advent of Keck telescope and VLTs, gravity interferometer, we have realized that the supermassive black hole sitting at the heart of our galaxy can be a naive probe for understanding gravitation. Zhang et al. Reported in 2015 through a simulation of 6 orbits of the S stars encircling the black hole, that if we have, that was a pure theoretical prediction, if we have an astrometric accuracy of 10 microarc second to measure the position of the stars near the black hole, and velocity accuracy of around 1 kilometer per second, these kind of observation will be able to determine spin of the black hole and mass of the black hole, and hence test the very theorem of the no-hair theorem of general relativity. This was a prediction in 2015. Spin and mass measurement, they are very important, simultaneous measurement, because of the no-hair theorem. If you get something different from no-hair theorem, that may be a signal for violation of GR. Then in 2019, people have used VLT to test local position invariance. And this is another foundational principle of GR. What is local position invariance? Laws of physics or physical processes are invariant with respect to position in the gravitational field. What VLT has measured, they have observed the hydrogen and helium absorption lines coming from stars moving near the black hole as they traverses different regions of the gravitational potential across the black hole. And we have not found any deviation of the absorption lines in strong field as well as in the weak field. So that means LPI is preserved. So that is the test reported in 2019. Gravitational redshift of light coming from SO2. The most studied star since 1990s till 2020 is SO2. You can call it S02. This is a nomenclature given by Keck telescope. If you have a VLT measurement, they have a different nomenclature, they call it as S2. So S02 star has been used to estimate the gravitational redshift coming from the star, and it has been measured by gravity collaboration 2019. Then Schwarzschild pericenter shift of the star has also been measured by gravity detector. Exactly, it happens like Mercury in our solar system. The star undergoes Schwarzschild precession that has been measured. So this doesn't say that GR is correct, but this says that it is very possible to test a theory of gravitation near the supermassive black hole. Massive gravity theory, where your Newtonian potential has some IUCAA correction, that has also been constrained by 2 stars. One is S02, one is S038. And the Keck group reported that massive gravitation theory can be constrained by using the stellar orbits near the supermassive black hole. Now let me come to the question in the morning session. Is there any serious alternatives to general relativity? In 2018, there was a calculation which says that FR gravitation theory is a natural outcome of geometrical correction to quantum fluctuations that is going on at the neighborhood of the event horizon of the black hole. And the Einstein-Hilbert action can be naturally constructed out of these fluctuations. And the fluctuation is written in a novel way as a summation over the fluctuation momentum k, vacuum fluctuation momentum k, and different powers of the Ricci scalar. For example, n equal to 0 gives cosmological constant because it is a constant term that we call constant vacuum energy density. N equal to 1 gives the linear term in the Ricci scalar, it gives general relativity. If n equal to 2, it gives Tarowinski inflation. So this in general we call power law gravitation theory. If we take weak field limit of this theory, we get a IUCAA correction that has been shown in this second equation. We call that IUCAA mode as a scalaron mode. It's a scalar field. M psi is the mass of the scalaron. If M psi is infinity, very massive, then it looks exactly like Newton. If M psi is very low, you will get drastic deviation from Newtonian gravity. That means breakdown of general relativity. Let us have a flashback on FR gravity. It explains cosmic inflation as mentioned by Abhijit without incorporating negative pressure. That was worked out by Tarowinski. For model building of the accelerated expansion, people use FR gravity theory without incorporating dark energy equation of state. We can also explain the flat rotation curves of galaxies without incorporating dark matter. This is preliminary reason why we believe that FR gravity might be a serious alternative to general relativity. But there is something more, why we think that it should be the case. Now I have 4 forecasts near the galactic center black hole. In 2020, calculation was done to show the barycenter shift of compact stellar orbits, much tighter orbits than S2. If we go down towards the left side of the x-axis, if the scalars are quite light, say 10 per minus 21 or minus 20 or minus 21 electron volt, then we can see that these scalars can destroy ZR towards the scale of S2, which is very risky because in S2's case, the short cell precision has already been measured and is found to be perfectly okay with GR. That means scalars should be massive relative to 10 to the power minus 21 electron volt. If we go to 10 to the power minus 20, minus 19 electron volt scalars, then we see that they are suppressed towards larger scales and ZR is winning, but towards the compact scale, this is the semi-major axis of the stellar orbits, and that is arc-second per year, the very center shift of compact stellar orbits. Arc-second per year.
This is actual measurement.
No, this is theoretical prediction.
No, I mean, this is actually what we do, not the deviation of it.
Not deviation.
Not deviation from GR.
Not deviation from here. This is theta, very center shift in FR gravity. That means the massive scalars are showing their effect towards the compact orbit, much compact orbit. You have to go perhaps below 200 AU. But the semi-major axis of SO2 is 970 AU, or like 1000 AU. 200 AU is not yet explored, neither by Keck nor by VLT. Perhaps that will be possible through 20 meter telescope.
Which is the GR, the largest mass?
The largest mass is acting like GR in large scale.
So where is that?
I have not plotted the GR graph here. I have plotted only effort for different scalar masses. So that is one effect. In both low eccentricity as well as high eccentricity, we see the general feature that massive scalars may show effect towards the compact stellar orbits. That was one focus, why we should explore compact orbits. Focus 2 is, if we have astrometric accuracy of the upcoming telescopes in the range 10 to 100 microarc second, it will be eligible to probe scalars both 10 to the power minus 22 to 10 to the power minus 18 electron volt within semi-major axis of 74 to 433 AU, quite tighter orbits. How did I do that? The query center shift in scalar gravity was equated to the post-Schwarzschild effect. What is the post-Schwarzschild effect? Spin effect, frame dragging, and any other correction that you have, which are quite tiny compared to the Schwarzschild effect. Because we should not equate to the Schwarzschild effect, because that is the master term. So these are other smaller terms, the spin and quadruple effect to the pericenter shift, to get the effect of, to see what kind of spin or what kind of semi-major axis will be eligible to probe that kind of scalars. Because in the master equation, the pericenter shift in FR gravity, scalar mass is the only parameter. For the revised version that is going to be published shortly of the detailed science case. Now what is the focus for TMT? It will be able to reveal heavy scalars, as heavy as 10 to the power minus 16 electron volt. Now 10 to the power minus 16 electron volt has other cosmological importance. We call it as ultra-light dark matter. We are not getting any signature of dark matter, assuming it to be heavy particles like WIMPs, neither in laboratory nor in the sky. So now people are working on ultra-light dark matter, which may show some effect in the large-scale structure of the universe. The third forecast, drastic departure from ZR is expected to be revealed below 45 AU. So we are looking forward to that kind of scale from TMT or other extremely large telescopes, maybe 40 meter plus. Looking forward, I am going to conclude by two-line summary. Possibly there is a close counterpart of ZR. We have to keep our mind open. It may be ruled out, it may be established. We are keeping our mind open. Therefore, we call for additional measurements through Astronomy's new generation telescope, the 30-meter telescope, so that we can understand this mysterious force of gravitation better. This is the Mizoram sky we captured yesterday from the helipad. Why I have shown this? We have little bit of dark cloud in the knowledge of gravitation. We have to remove it. Then perhaps we can see the brightness. Thank you.
Small felicitation. So, Dr. Sanjeev's first research scholar, Duarte, will felicitate you.
Oh, you are always in the advantageous position. Thank you so much.
It's like this.
Yeah, like Thank you, Rati. Thank you, Sanjeev.
Thank you.
So the next speaker is Ritik Bora from Tezpur University.
Good afternoon everyone. I'm Ritik Bora. He is a student in the Department of Physics, Tezpur University. So at the outset, I'd like to thank Mizoram University for giving me an opportunity to deliver a talk on the basis of a recent work that we have done. So this work has been carried out in collaboration with Professor Ranjit Mishra, Dr. Rukia Khanun, and Dr. Rupajiko. So this is the title of my talk, Jet Pod of Mercurian 501 from broadband acidity modeling for different spectral models. So moving ahead, this is the outline. I will be briefly introducing to AGN, laser and some radiative processes, and followed by the motivation, and the process that we have used to do the data analysis and the spectral analysis, and the models that we have used, and finally the results and the concluding remarks. So I will not be going in details as we are well aware what an active galactic nuclei is. So it's a bright center of a galaxy which has energy anywhere in the range more than 10 to the 40 arcs, and has a characteristic of emitting the light in radio to high energy gamma rays across the whole EM spectrum, and it's thought to getting powered by supermassive black hole at the center, which is mass more than 10 to the 6 solar masses. And below is a cartoon which explains the classification of an AGN, and one of the classification, that is the blazer, which is the jet that directly pointed towards the observer, which is a region which in the order of 10 to the minus 3 parsecs in size, and it emits the photons in the whole EM spectrum, and with other elementary particles like electron, positrons, and recently the neutrino has also been detected from blazer, and also the list is not yet full, so maybe in future we might detect some other particles too. And as a characteristic, it shows rapid variability when we do some temporal study, timing study, and it has non-thermal emission. And behind the non-thermal emission is mostly the synchrotron radiation. And to explain the acidities of blazars, there is a two-hump structure that will be coming. I'll be coming after some time. And to explain the high energy hump, there is a process associated with the inverse Compton radiation. And one other is the synchrotron self-Compton radiation, where the electron population that are responsible for synchrotron emissions scatter the photons to very high energies. And another is the external Compton, where the photons that are produced outside the emission region are scattered to very high energies by inverse Compton process. So coming to the most important blazer properties is the double hump of blazer, and another is the curvature in spectral energy distribution. So in the cartoon that you can see, there is a one represented by red and green. So the red one is HBL. This is the high synchrotron peak blazer, which is the first peak in the frequency range around 10 to the 15, and this peak is thought to be emitted because of the synchrotron emission, and a high energy peak is assumed to be due to the inverse Compton emission. And for the green, this is associated with low synchrotron peak blazer, which is also the same mechanism is associated with it, but at a less frequency. And next is a curvature in the spectral energy distribution. This is a plot of Mercurium 421. It is a well-studied source, and it's initially it was thought to be fitted by a parallel, but there is when people studied the source extensively, then they found a curvature in this spectral energy distribution, and finally a curvature parameter has been introduced in the parallel, and this is fitted with a log parabola function. Next is the motivation, the general motivation of studying blazars. So to understand the jet creation and its origin, and the location where the emission region is located and how the particles are getting accelerated to high energies, and also to measure the energy densities of particles, magnetic fields, and etc. And how to achieve this objective? We do spectral and temporal study. We do data analysis using various softwares, and try and finally develop some physical models that explain the spectral energy distribution of particles. So to go ahead with the objectives, so we have considered the source Markarian 501. So it's a HBL source which has a peak frequency more than 10 to the power 15 Hz, and it is a redshift of 0.034, and the location is given by this arrow index. And as the blazar emits in the whole EM spectrum, so we have considered observation from UV to gamma rays. So for studying the X-rays, we have considered NuSTAR, Nuclear Spectroscopic Telescope Array. So it used to study the X-ray in the range from 3 to 79 keV, and it has two focal plane modules, FPM and FPMB, and this is the cartoon which shows the NuSTAR in NuSTAR configurations. And next, we have used SWIFT, which has three instruments basically: Burst Stellar Telescope, X-ray telescope, and ultraviolet optical telescope. So we have used SWIFT XRT to study the X-ray in 0.2 10 keV, and we have used SWIFT UVOT to study the UV counterpart. And it has 6 filters in optical BVU and W1, W2, and M2 in the UV filters. And detection wavelength range is 170 to 600 nanometers. Now finally, we have, for the gamma rays, we have considered Fermi-LAT, the large area telescope, to which detection the 20 MeV to 300 GeV. It's an all-sky survey which used to study AG and pulsars, etc. And these are the observations that we have considered from 2013 to 2022. Although it's scattered, so corresponding to the NuSTAR observation, we have considered SWIFT XRT and UVOT, and for the Fermi, we have considered 4 months data in each NuSTAR counterpart. And data analysis, we have used the standard procedure to analyze the data for NuSTAR and for SWIFT also. So, but SWIFT we have also looked for pile-up corrections, because it's something like when multiple photon detects in the CCD, so we get pile-up. So we have removed pile-up from few of the observations. Then for the UVOT, the rating correction and the rating correction and all the other standard procedures has been carried out. And for the Fermi-LAT also, we have done using the standard procedure. And to if someone is interested to follow the Fermi analysis, then can follow this link that I've given below. The next is the spectral analysis. So we have considered spherical region of radius R, which is filled with magnetic field B and isotropic electron distribution. So basically, we have considered a leptonic model to explain the acidity of the blazar. Then we have included local model in XSPEC, the X-ray spectral fitting package. This is called synchrotron convolution model. And to finally fit the gamma rays, because this will only fit the UV and X-ray part. To fit the gamma rays, we have used a Broadman model called SSCICON. This is also a local model, which is convolved with other particle distribution represented by n of chi. And to account the collective absorption, we have considered the T-waves model. And for this source, the NX is given by this given below. So we have firstly used the spectral model, the log parabola model, as I have already mentioned in the previous slide. So this is the equation to gives the particle distribution, where the alpha is the spectral and index and the beta is the curvature parameter. So the beta parameter used to actually explain the smooth curvature that we get in the acidity of a blazar. So this is a base fit parameter table that you can see. So we consider 10 observations. So we have fitted the observation with the spectral index, beta, the magnetic field, the size of the emission region, and jet power, and also the fitting is ensured by the reduced chi-square, which is given in the last column. Then we assumed a model called particle distribution with a maximum energy, chi-max model, and the particle distribution here is given by the equation 4, and it is the intensity is associated with acceleration time scale and escape time scale of the particles, and also it has another terms which are related by which are explained the cooling term and all, chi-max which is associated with a factor called C, which is associated by this relation, and also the max term, gamma max term, which is associated with the cooling term by this relation. So below is the fit parameters again for this model also. Then next we have assumed the scenario where the particles are energy of the particles are dependent on diffusion, and this is the relation where this is the particle distribution relation given by equation 6, and below is the fit parameters, and another scenario where we have assumed the energy dependent to the energy of the particles are acceleration dependent, and below is the similarly it's the base fit parameters we have obtained, and finally we have used the broken power law distribution to fit the observed data, and this is given by P and Q, which are two spectral index, because it's a break in the spectrum and it has energy break. So we get two spectral index, electron spectral index here, and there is a break in energy parameter. So the parameter number of parameter get increased by 2, but and this is the best fit table for this global power distribution. So this is the final plot, the fitting that we have obtained. So this plot represents the swift UVOT which are given by the black dots in the frequency range 10 to the power 15. Then the swift XRT is represented by these orange points, and the booster FPM and FPMB, the two instruments which are represented by blue and red, and finally the black, the Fermi, the gamma rays are represented by these black points in the 10 to the power 22 to 26 parts. So all the models are represented, the broken power, log parabola, gamma max, and EDA and EDD models. So it seems that all the models are fitting the observation preferably in a better way. And this is a particular observation in 2017. So I have shown only one observation here, as it will take much time to show all the observations fitting. Then next we have looked into another parameter, the jet power, that mostly were interested to look after. So this is a jet power variation plot. We have so for this is for a particular for all the observation. So the points represents for 10 observation, and the models are for all the models it is plotted. And we have seen that for log parabola model the jet power is the minimum, and for EDA and EDD model the jet power are marginally the same. And as we have a parameter called gamma min, the minimum electron energy for broken power distribution, so we have varied that parameter and found that jet power are varying by some factor of 2. So while increasing the gamma min value, so the jet power is getting reduced by a factor. So this is basically the gamma min and the jet power. So we have ensured that the chi-square shouldn't go back, because once we change the parameter while fitting, the chi-square of fitting also goes back. So we have also ensured that beyond that value of gamma min, we just put a constraint, and so it significantly reduced for the broken power distribution. And finally, this is a plot for the Lorentz factor. So we have varied the Lorentz factor and found that the jet power varies very marginally. The left plot is the broken power law, and the right one is the log parabola. So this is so this has a very little contribution from bulk Lorentz factor. So yes, so this work we have submitted and it's under review in MNRS. So conclusion finally, so for broken power law and gamma max model, so we have found a jet pulse as high as 10 to the power 47 hours per second, and for high values of gamma min, the jet pulse significantly reduced to 10 to the power 44 hours per second, and marginal change in the jet power as we increase the Lorentz factor. And to understand the comprehensive picture and microphysics behind the jet power variation, so we will look into other sources like FSRQs and extreme VLX. So yes, this is your references. Thank you so much.
Good afternoon, everyone. I'm Isel Tantuono from Tezpur University, and today I will talk about the long-term study of broadband variability in signal section using AstroSet, and these are the contents of my presentation. And for the source, signal section is the first object identified as a black hole, and it is an X-ray binary source. And black hole X-ray binaries arguably provide wonderful opportunities to understand accretion dynamics. And in black hole X-ray binaries, matter from companions are forming accretion disk around the black hole, and matter loses angular momentum within the disk through viscous dissipation, which cause inward drift, heating, and emission of radiation. And radiation emanating from this in proximity to the black hole has significant strong gravity. And persistently bright black hole X-ray binaries exhibit two spectral states, which are high soft states and low hard states. And in the study carried out by Ankur Kushwaha, he mentioned that in 2016 the source is in a low hard state, and in 2017 for about 7 months, that is from March to September, the source completely transits to high soft state, and the source passes through intermediate states and remains in the soft state for about 2 months. And from November onwards, the source transitions back to low hard states. And for the observation and data reduction, we focus on 4 observations undertaken in 2016 and 2017 respectively. And LexPC covers an energy range of 3 to 80 kV, and SXT covers an energy range of 0.3 to 8 kV. And analysis of both LexPC and SXT were done using LexPC software and LexAid respectively. And SXT event merger tools were used to create the merged event files from the clean event files, and spectra were fed using expect command. And for power density spectrum, Fourier transform is widely used in timing analysis, and Fourier transform plays a crucial role in timing analysis by providing a powerful tool to analyze and understand the frequency characteristics of the signal. And in astronomy, the light curve represents the variation in brightness of an astronomical object over time. By performing an fast Fourier transform, we can analyze its frequency content, which can provide insights into the periodic and quasi-periodic variations in the intensity of the light. And power density spectrum is the measure of the distribution of power across frequency in a signal. And PDS provide information about how power of the signal is distributed across its frequency components. And in this work, we use the energy range 4 to 80 kV to construct power density spectra for all the observation. And in 2016 observation, we took the energy range from 0.02 to 11, and in 2017 observation, we took the energy range from 0.2 to 15, and 3% systematic error were added in 2016 and 2017 power density spectrum fitting. And these are power density spectrum from 2016. The first one is taken, which is taken in January, and the second one is taken in June. And you can see that January observation is showing 2 peak features here, and June observation is showing 3 peak features here. And for 2017 observation, it's still the same as for 2016 observation. And in March, the PDS is showing 2 broad features here, and in September, it's showing 3 peak features here. One is there, and 2 and 3 is there. And for the analysis, for both the observation, we have taken the energy range to be 4 to 50 for Lex PC and 1 to 7 for XXT, and we set the energies with 0.01 500 log, and we fitted the combined spectra of the observation with a model consisting of interstellar absorption, a simple Gaussian line, thermal components component, and multi-black body components, which are represented by expect models, TBEPS, Gaussian, ESCOM, and this BB. And we use this combination in the expect for fitting this, to do the spectral fitting, and 3% systematic error were included in the spectral fitting. And these are the results of spectral fitting for 2016 observation. The left one is for January, and the right side is for June. And these are the spectral fit parameters for 2016 observation. And we get the chi-square around 0.8 for January and 1.1 for June observation. And for 2017 observation, this is the combined spectra for signal 6 and these are the spectral fit parameters for 2017 observation. And we get the chi-square around 0.5 and 0.6. And for the discussion, in January 2016 and March 2017 observation, the PDS is showing 2 peak features, and we fitted them using 2 Lorentzian. And in June 2016 and September 2017 observation, the PDS is showing 3 peak features, and we fitted them using 3 Lorentzian. And Gaussian was kept frozen at 6.4 keV for all the spectral fittings. And again, correction was applied to the S60 spectrum using expect command gain fit, where the slope was fixed at unity. And in 2017 spectral fitting, there could be a second coronal, and since we're getting some residuals, and we used 2TH model to fit the parameters. Here you can see that we use 2TH model here, and the one which have low output values, we freeze them, and we get best fitting for this observation. And for our future works, we are planning to do timing fitting for RMS and electric fitting by using a Garket model. And we are planning to use the observation from 2016 to 2019 whole observation, which are available in AstroSet. And that is my presentation. Thank you.
Hello everyone, my name is Vicky Prasad, and I'm doing PhD under Dr. Tezpur Das in Assam University. And the title of my talk is Study of Polarization Properties of Asteroid and their Compositional Type using a new empirical formula. In this work, we basically study the parametric properties of asteroids and lunar soil samples using a new empirical formula, which is basically used to get a reliable fitting of phase polarization curve of asteroids and other atmosphere-less polarization bodies. And in this work, we analyze various asteroids and their composition types using the formula. And you use this formula to extract some properties of phase motion curve of different asteroids of various types, and we find the correlations of the properties with the geometric albedo of different types of asteroids, and we use these correlations to verify the Umhoff law, and by the results we can suggest a new classical scheme of asteroids based on the parametric properties of asteroids. So first of all, the asteroids are the small atmospherical bodies which is not changing. Okay, so on the basis of their composition, so asteroid can classify in three major categories. So as C-type, S-type, and M-type. And C-types are basically they are carbonious, and they are the majority of asteroids in our solar system. And 75% of asteroids we have been observed till now are found to be belongs to C-type. And another type is S-type, which contains silicates, and it is about 17% of the asteroids in our solar system. And the third one is very rare, which is M-type, and they are metallics. So there are another scheme of classification of asteroids, which is based on the spectroscopy. But in this study, we not considering the spectroscopy-based classification, and we try to in this work we suggest a new scheme which is based on parametric study. We can using the parametric properties we can classify asteroids. Because it is very difficult to get the spectroscopy of asteroids because they are very faint objects. So we use parametric study. So first, as we know, there is always a chance to collide asteroid to Earth or collide with our artificial satellites or spacecraft. So it is very important to track the path of asteroid. So like recently, so I think we all heard about the recent mission, DART mission of NASA, which is altered a path of an asteroid. In this figure, we can see two double asteroid, which is this one is revolving the other asteroid. There are two paths, and a white one and blue one. And the white path is the before the path or before impact, and after impact, the path is slightly changed. So there are various importance among them. Recently, in the a total number of 23 amino acids were found in asteroid sample DAY-2. Okay, brought back by Japan's Hayabusa 2 spacecraft. So we know that amino acids are the building blocks of proteins, which is the basis of life in a planet. So this is diagram. This is a photo of a UV asteroid, which is taken by the Hayabusa 2 space probe. So the other picture is some samples which is brought back by the spacecraft. Also, recently, yeah. So this is a artistic impression of asteroid site. It's not a actual image. So this asteroid is M-type asteroid, and it is made of metals about 60%, like nickel, iron, and gold. So in our study, we study the phase polarization curve of asteroid, and the polarization of asteroid or other atmosphere-less bodies we can present using this relation. So here PR is the linear polarization of scattered sunlight, and I perpendicular and I parallel are the intensities of the scattered radiation in the perpendicular to the scattering plane, and the other one is the parallel to the scattering plane. So in this figure, this is a schematic diagram of a phase polarization curve. So it is observed that in phase angle less than around 20, the I parallel is found to be greater than I perpendicular. So in this region, we get a negative sign in this equation, and this polarization is called negative polarization. And after that region, I parallel is become less than I perpendicular, and we get some positive signs. Then beyond the inversion angle, we get positive polarization. And that angle where in the diagram we see that the polarizations become negative to positive at a particular angle. This angle is known as inversion angle. And it is for asteroid, we have only data up to 27 degree phase angle, because asteroid is very faint object, so from ground based observation it is very difficult to obtain the data beyond 27 degree. So to analyze this phase curve asteroid, so various researchers provide some various empirical formula or relation between polarization as a function of phase angle. Here P as a function of phase angle, and these formulas are derived by different scientists in different times. Okay, these formulas have some limitations because if we see equation 2, this equation is valid till 30 degree phase angle, and equation 2 and 3, and equation 1 and 4. There are limitations like if we have very less number of data points, the accuracy is not so good. So in our work, we modify equation 1, which is given by Lumin and Mion in 1993, to get some better approximation. We take some modifications, which are and this we after modify we get equation 5a. And also this equation is we can also represent this equation in terms of slope and inversion angle is like equation 5b. So basically two equations are same equations. Okay, so 5a and 5b are the two same equations in different parameters. So if we have data, if we have inversion angle, then we go with equation 5b, and if we have we does not have h, then we can take equation 5. So basically in this work we use to fit the phase angle phase curve. So we take nonlinear least square fittings, and the algorithm is based on Leavenworth-Margulis algorithm, and also we done Monte Carlo simulations to calculate the errors in Pmax and Pmin. So these are some results which of phase polarization curve of lunar soil sample, which is portrayed from the Luna 24 and Apollo 16 probe. So from this this relationship, these data are taken in various bands. We see different lambda. So if we put Pmax versus lambda, then we get a very interesting correlation. So we can see that the Pmax is correlated with lambda. Okay, these are the polarity phase curve of different types, some different types of asteroid. We take actually we done more than 200 polarity study of 200 asteroids, but we just present in this in 3 asteroids. So one is first is C type and M type and S type. So we can see the difference. So the C type asteroids have the the greater value of Pmax, and the S type asteroids have greater value less value of Pmax and Pmin. So we can see the difference in 3 plots. So 2 plots are same. This plot is just from 0 to 30 degree. Okay, and this is the phase polarization curve for asteroid Phaethon, and this is the interesting little asteroid because this is the only asteroid till now which we have the phase angle 0 to 120, 135 phase angle. So this is the only asteroid till now. So in this asteroid we find the some properties like Pmin, Pmax, and in two bands, R band and P band. So results are shown in the table. So from our observations, we get some very interesting results. So this plot shows the correlation between Pmin and albedo of different types of asteroid. So we can see that the green and red and blue are representing the three different types of asteroid, C and M type and S type asteroid. So we exactly we can see that the three we can, if we plot log Pmin and versus log A, we take the modulus because Pmin is always negative. So for log scale we take modulus, and we see that. So if we know the polarization Pmin, then we can find the and if we have the value of albedo, then we can classify the asteroid in three different types. So in there is a box in this plot. This is from the region where M types of asteroid belongs. Some dots we can see that some red dots are outside the box. This is because we have very less number of M type asteroid data, and also there are some errors in the calculations, so we get some deviation. And this picture we plot Pmax and Pmin. Also we can get same type of result. Here we take negative because if we plot Pmax and Pmin exactly, then we get a negative slope because of we can't take log of Pmin because it is always it is negative quantity. So to visualize the slope, we just take negative of log Pmin. This is the correlation between Pmax and albedo. Also, we get same type of results. So, if we observe three types of plots, then we can see that. So, different types of asteroid can be located in different positions of this plot. So, using this, we can suggest a new classification scheme which is based on the polarization property of asteroid. So this is the first time. This is the first attempt to classify the asteroids in polarization property. There is a classification based on spectroscopy and photometry. This is the first time to classification based on parametry. So summary and conclusion of this. So in this work, we develop a new empirical formula to study the parametric properties of asteroid, and also we verify this formula using the samples, lunar samples, which is brought back from Luna 24 and Apollo 16 probes. And this equation, we can use this equation to find various correlation between Pmin, Pmax with albedo. And also, using this equation, we can classify the asteroid based on parametric property. Also, we report this work in MNR journal, which is under review now. So, thank you.
This talk is based on two of my research papers. The first one being the modification of the inflationary gravitational wave spectrum due to the electron-positron annihilation, and the second one is due to the cosmological phase transitions, which are electroweak phase transition and the quark-gluon plasma to hadron gas phase transition. So first of all, the evolution of the universe can be divided into 5 stages, and here the second stage, the reheating stage, is the stage where the scalar field
which is usually called the inflaton, which drives the inflation, decays into radiation and reheats the universe. And the accelerating stage is the current stage that we are in, and the radiation dominated stage can be usually divided into several other stages where several events happen. The standard model predicts several events, some of which are the electroweak phase transition, the quark-gluon plasma to hadron gas phase transition, and there's also neutrino decoupling or neutrino free streaming, and several of the models beyond standard model predict some phase transitions like Pechet-Quinn phase transitions, which predicts a hypothetical particle called axion and supersymmetric breaking. But here we are going to deal with the electron-positron phase, the electron-positron annihilation, the electroweak phase transition, and the QGP phase transition. So these events within the radiation-dominated stage are inserted in the third stage here. So we have several stages, including these additional stages, and each of these stages are joined by the scale factors and their derivatives. So using the scale factor and their derivatives, we get the continuity equations with which we can obtain all of these parameters, like the constants and the inflationary index and the reheating index and the other indices which characterize the phase transitions. And I'm only showing one of them, which is the last one, L0. From this we can get the normalization and the reheating index. So this the first equation here shows the perturbation matrix, where we have included the tensor perturbation, which is the gravitational waves. And this tensor perturbation can be decomposed into Fourier modes, and this Fourier modes, again after rescaling, reduces to an equation which is equivalent to a one-dimensional oscillator. So a one-dimensional oscillator in a potential barrier, and the second term within the bracket is the height of the potential barrier. So during the inflation, the primordial gravitational waves arise from the quantum fluctuations from the initial vacuum state, which, on interaction with the variable gravitational field of the early universe, and gets transformed into a multi-particle quantum state. So here we have the initial amplitude of the primordial gravitational waves, and the term A here is the normalization. And for the normalization, I'm using the data from the joint collaboration of Bicep-Keck and Planck, which is released in late 2021. And for this normalization, it is assumed that the CMB anisotropies at lower multiples are partly induced by the primordial gravitational waves. So from there, I calculated the CMB anisotropies around multiple AC, and from that I get the normalization constant. So in the lower frequency region, or the longer wavelength region, the wave is inside the barrier, the wave is inside the potential barrier. Therefore, the amplitude can be approximated as constant. Therefore, here I'm taking that the amplitude remains the same as the initial one. However, for the rest of the frequency ranges, that is for the higher frequency ranges, the wave mode is the wave field is already outside the potential barrier, so it propagates with a gradually decreasing amplitude. And the decreasing amplitude, the decreasing factor here is also calculated from, again, the continuity condition. And the amplitude, so here we have the amplitude for each of the stages from the lowest frequency range to the highest frequency range. And K1 here, the last K1 here in the last equation is the wave number corresponding to the reheating stage, the start of the reheating stage. So for the model, I'm using the R-square inflation model, and this prediction of this model is valid for higher values of the E-folding number. Here I'm choosing E-folding number 60, which means that during the inflation, a patch of space-time increases by a factor of e raised to 60, which is equivalent to 10 raised to 26. So resultant inflation kanin patch of space-time ka 10 raised to 26 in a point so that is the essence of inflation in result. And so for this particular model, the tensor to scalar ratio is 0.0033. And here we have the tensor spectral index. The tensor spectral index related to the inflationary index. This is calculated from again the power spectrum. Here, moving back. So here from equation 1, the initial amplitude is directly proportional to k raised to 2 plus beta, beta being the inflationary index, and the amplitude squared is equivalent to the power spectrum. So the power spectrum is directly proportional to k raised to 4 plus 2 beta. And from the usual primordial gravitational wave power spectrum relation, we have power spectrum of the tensor modes directly proportional to k raised to nt, which is the tensor spectral index. So from that we get this particular relationship, and this particular relationship leads to the inflationary index being minus 2.0021, and the first reheating index is calculated without considering the phase transition, and when the phase transitions are included, I get a little bit higher, and the tensor spectral the reheating index without considering the phase transition is calculated from these 5 stages only. So I get fewer parameters in the expression for L0 here. So this is how I get a lower value. And the energy density here is the energy in the inflationary gravitational waves for a given volume in a given space as a function of frequency. And in the absence of the phase transitions, the inflationary gravitational wave is expected to give a result to a scale invariant spectrum, which is the dashed line here. And however, in the presence of the phase transitions, we get steps. This is because during the phase transitions or during the electron positron annihilation, there's reduction in the number of reduction in the number of relativistic degrees of freedom. This directly affects the rate of growth of the Hubble radius, which also directly affects the rate of horizon reentry of the particles. So the horizon reentry of the modes, which also reduces the spectrum. So this is the change in the energy density per logarithmic frequency interval, and so I don't see point of view. So for only the electroweak phase transition, the reduction in the energy density is about 3%, close to 3%, and for only the electron positron annihilation, the reduction in the energy density is 25%, close to 25%, and for QGP phase transition is close to 35%, and for the overall with the overall phase transition, the reduction is about 63%. And in the case of the amplitude, the change per logarithmic frequency interval is 1.5% for the electronic phase transition, 12% for the electron-positron phase transition, annihilation, and 80% for quantum for quark-gluon plasma to hadron gas phase transition, and around 31 or 32% for the overall phase transitions or events. So this is the amplitude per root hertz plotted with the sensitivity curves, and except for the international pulsar timing array, the others are the upcoming or proposed detectors, and the amplitude, or even if I also plot it with the energy density, I'll also get the same results. That is the spectrum is within the sensitivity curves of square kilometer array experiment, Big Bang observer, and DAY-2. However, the problem with this is that the wavelength of the inflationary gravitational waves is about 10 raised to 26 meter, which is close to the size of the observable universe. So even if the amplitude and the energy density, are inside the sensitivity curves of these experiments, it is unclear whether they will be able to be detected. And not only because of the large wavelength, they may be also buried within the many sources of gravitational waves from cosmological or astrophysical sources. However, there are also some theoretically proposed detectors which would be operating in higher frequency regions, and these experiments or detectors given here operate at lower frequency range than those of LIGO, Cosmic Explorer, and Virgo, and the others. However, there are theoretical proposals for detectors which would be operating at an even higher frequency order frequency region. So there may also be some prospect of detection. so that is the end of my talk.
Okay, so a very good afternoon to you all. I am Ruchoti from Tezpur University, Assam. And first of all, I would like to thank the organizers for organizing NEMA-IX, and also for extending their invitation to me and to all of us. NEMA is very close to heart, so whenever we get an invitation for NEMA, it's very difficult to say no. So I will be talking about our efforts towards investigating the origin of diffuse far ultraviolet emission in galaxies. This is a collaborative work which I am doing in collaboration with my long-time collaborator, Dr. P. Shalima from Manipal Center for Natural Sciences under Manipal Academy of Higher Education, and from time to time different MSc and PhD students are involved in this work. So basically we are investigating the FUV background in galaxies, in our own galaxy and also in some external galaxies. So when I say diffuse, I mean the sky without the stars. So when we throw away all stars of the sky, that is the background. So that is actually a continuum with ranges over different wavelengths, but we are focused in the far ultraviolet region of the background radiation. So what we are trying to see is that we are trying to see how much the dust scattered light can account for the diffuse far ultraviolet background in galaxies. So this we call as diffuse galactic light, DGL, This is one of the components. There are some other components like EBL, extragalactic background light, the light from other galaxies, and also there are some other components which collectively is known as offset. But we are only interested to see to how much the dust scattered light can explain the diffuse far ultraviolet background. And we consider only star forming region, locations near star forming region. So, since there are people from different backgrounds, there are students as well. That's why, first of all, I would like to introduce to you the interstellar dust grains, the importance, composition, and the life cycle of dust grains. Then, little bit about effects of dust like scattering and extinction. Then I will introduce to you the scattering model which we are using. We are actually using different models, but here I'll be explaining just a single model. And finally, if time permits, then I will speak about application of the model to some specific location. Well, to start with, when we say interstellar medium, we refer to the space between the stars, which is primarily gas and dust. So 99% of the ISM is gas. Gas in ionic, atomic or molecular form, and obviously primarily hydrogen and helium. And just 1% of the interstellar medium is dust. Now when I say dust, it may be sand-like or it may be soot-like, and they are tiny pieces of solid particles composed mainly of carbon, silicon and oxygen. Now, to understand how much fraction of a typical galaxy is dust, I am referring to a typical Milky Way type of galaxy. So in a typical Milky Way type of galaxy, roughly 1/6 of the total galaxy mass is baryonic. Out of that 1/6 is the interstellar medium, and in the interstellar medium, 1% or even less than 1% is the dust. So this is just a minuscule fraction, a very tiny fraction of a galaxy, yet it is very powerful. How powerful? We can understand from this figure. So here this portion is stellar emission. This is from the starlight which are there in the galaxy, and this portion is because of the emission by the dust grains in the galaxy. Stars in a galaxy, they emit mainly from UV to near IR. That starlight will be absorbed by the dust grains which are present here in the galaxy. They will reprocess the light, and that light is emitted in the infrared portion of the electromagnetic spectrum. To how much the light will be reprocessed and how it will be reprocessed, that will of course vary from galaxy to galaxy and also from location to location inside a particular galaxy, depending on what type of dust is there in that particular galaxy. Now the important point here is that we can see that 50% information, almost 50% information about the galaxy is hidden beneath the dusty layers of that galaxy. So we get secondary information about the galaxy if we study this light in the infrared portion. So this is such a tiny fraction in a galaxy, yet it's very powerful. So if we are interested in any facet of astronomy, then we just cannot ignore this tiny fraction. So that is the importance of interstellar dust grains. Now, it's not that only our Milky Way galaxy is dusty. These are some beautiful pictures of some external galaxies. So here we can see some dusty features. We can see some dust lands, spiral arm dust lands. So very beautiful dust rings we can see here. So it means that all galaxies are dusty. The type of dust, amount of dust will of course vary. But to study intrinsic galaxy properties, we need to account for the effects of dust. So that is the importance of the dust studies. Now coming to the composition, they are mainly solid particles of few micron size, primarily composed of elements that are abundant in the universe and in the interstellar medium, of course. So candidate constituents are carbon, oxygen, magnesium, silicon, sulfur, iron. They are comprised mainly of carbon and silicate. And 28% of dust mass we see in the form of carbon. Carbon may be in the form of solid carbon like graphite, diamond, or it may be in the form of hydrocarbons like polycyclic aromatic hydrocarbons. Those are some rings of hydrogen and carbon atom, I'll show you. And 72% in other compounds like silicates, oxides, like that. So this is the typical structure of a dust grain. It consists of a core. This core is about 0.05 micron, and it is sometimes of silicates, iron, or it may be carbonaceous. And the core is surrounded by an icy mantle. That mantle is formed out of water, ice, or anything like this. And the core and this icy mantle, it is surrounded by a sticky surface. So this is a sticky surface, and the surface of a dust grain, it actually works as a chemical factory in the sense that simple organic compounds can form on the surface of dust grain. As for example, here we can see two hydrogen atoms are combining to form one hydrogen molecule. So just like that, they act as chemical factories.
What is the typical size of the grain?
It's few micron, 0.05 to 1, like that, few micron. Well, so the life cycle of star is being discussed by many speakers, by Himadri sir, by Professor Pralay Karmakar also. Now, the life cycle of dust is very closely related to the life cycle of star. Actually, whenever life of a star ends, life of a dust grain starts. So, as discussed by the previous speakers, stars mainly form in nebula, which are very, which are regions of gas and cloud, very thick layers of gas and dust is there. So, inside those nebula, baby stars are being born. So, a protostar, once it is born, then it evolves through different stages of its life. That's why those nebula we call as stellar nurseries. So once a star is born, what type of life it will span, it depends on the mass of the star. So like if we have a very massive star, then finally at the end of its life, it will become a red supergiant. And average star like our sun, it will become a red giant. But whatever is the case, at the final stage, it will contribute materials into the interstellar space by injecting the stellar material into the medium surrounding the star. Like a red giant, it will just shed its outer layer into the interstellar space in the form of planetary nebula. And we know that if it is a very massive star, then its date is very beautiful. We see that supernova explosion, then we get supernova remnant. Whatever is the case, the dying star will enrich the surrounding medium with materials for the next generation of stars to form. So that's how dust grains are formed transformed and destructed inside galaxies. Now, once a dying star, it injects its inner material, then again we will get those nebula, those dark clouds, and again inside those nebula, new stars will born, and the whole thing will be repeated. The whole cycle will be repeated. Now, coming to the effects of dust, this thing was also explained by Himantri sir in his talk. So, dust grains, they scatter light, and they also absorb, and scattering and absorption with together, it is called as extinction. And here, similar kind of figure you have already seen in yesterday's talk. So we have an object here which is emitting light in different wavelengths. We have a cloud where we have some dust grains. So all these tiny white dots, they represent dust grains. Those dust grains will scatter the blue light very effectively or efficiently because of the size. The wavelength of blue light is comparable to the size of the dust grain, and that's why the red portion manages to pass through this dusty cloud, and observer on this side, for him, he will see this object as a redder object, which we call as reddening. So this extinction, it results in reduced intensity and reddening. So similar type of reddening we see when we enjoy the view of sunset near riverbank or seashore. There it happens because of those atmospheric dust particles, and here it happens because of the interstellar dust particles. So here we have a star on this side, we have a dusty cloud. So if we observe this star from this side with the help of some optical telescope, then we will not be able to see the star because the light will be blocked by this dusty cloud. But if we use some infrared telescope, then as I have mentioned in the earlier slide, then the star will appear as a radar star. And if we observe this cloud from this side, then we will see a very beautiful blue reflection nebula. So it matters from which side we are observing it. So interstellar dust, it actually betrays their presence in many different ways, sometimes by blocking light and sometimes by creating beautiful patterns, but they are responsible for creating all those beautiful images which we usually save as our wallpapers. So this interstellar reddening, it depends on the line of sight. Of course, more dust along the line of sight, there will be more reddening. So that is the reason why distant stars appear redder than the nearby ones. So it will vary from line to line. And these are some parameters which were also explained by speakers in yesterday's session. So color index of a star, color excess, and RV, all these are some parameters which we need for our work, which we use for our work. Now, just like the reddening, interstellar extinction, it will also vary with the line of sight. And every line of sight will have its own extinction law. Now, if we plot extinction as a function of wavelength, then we will see some pattern like this, where we notice some bump around 2175 angstrom. So this 2175 angstrom, it is attributed to the presence of polycyclic aromatic hydrocarbons. And if we compare the extinction curves for Milky Way and our neighboring galaxies LMC and SMC, we see something like this. The extinction curve for Milky Way, which is shown here by this pink colored dotted line, and for the LMC, it is being shown by these red dots and blue dots. So it's quite similar, it's quite close. But if we see the extinction curve for SMC, small Magellanic Cloud, then we see that it's almost flat. The 2175 angstrom bump is not there. So the type of dust which is present in Milky Way and LMC, they are kind of similar, and maybe the dust which is there In the SMC, it's different. The dust which is there in Milky Way and LMC. So this kind of work actually we are doing. Now, I have mentioned about these polycyclic aromatic hydrocarbons. As I have mentioned, they are collection of benzene rings, 2 or more aromatic benzene rings. They are fused together, and they show characteristic emission features at different infrared wavelengths. And these PAHs, they may also form some clusters. Those clusters are called as very small grains, VHGs. So VHGs are clusters, and they are more stable than individual PAS molecules in regions of high radiation field. And they exist in the center of H2 region. That's what observation says. Well, so now coming towards the model, I would like to mention about the factors which will be affecting the scattering. Of course, the composition, size and shape of the dust grain, it matters a lot. So it's a very important factor. Then we have this phase function asymmetry factor. This phase function asymmetry factor G, it tells us whether the scattering is isotropic or backscattering or forward scattering. And then we use scattering phase function proposed by Heine-Greenstein. So this is used to calculate the direction of a photon once it suffers a once it encounters with a dust grain. Then albedo, it is the ratio of scattered to incident intensity. So of course it will vary between 0 and 1. Dust distribution is a very important factor. So
maybe anisotropy also might be.
Yeah. So dust distribution will also matter here, and we should know the relative geometry of the stars in the dust, where the dusty layers are there and where the stars are placed.
What is the albedo term in this equation? Is it there?
Which one? This one? No, here it's not there. This is just used to calculate a new direction in the model. Whenever the photon encounters a dust grain.
What about albedo in your modeling?
We used to vary in a direction.
Parameter.
Yes.
Parameter.
Yes. Well, so the model is pretty simple. What we do is that the galaxy we are studying, or the region which we are studying, we just divide it into some boxes. So this is such a box. So inside this box, all these blue circles, these are the dust grains. So a photon comes like this. Then, it encounters with a dust grain. Then it takes a new direction. So here comes this phase function. This phase function is used to calculate the new direction of the photon. And when it interacts with a grain, its effective weight is reduced by a factor of the dust grain albedo. Now, here we can consider two cases. Number one, for optically thin medium, we consider single scattering. Means we considered a single photon will just suffer one scattering. And we can also consider a multiple scattering model where we consider that scattering continues until it either leaves the area under consideration or its intensity drops to some negligible value which we can put as some parameter. So these are the input parameters.
So in your modeling, you are doing with single scatters?
Actually, we try both. But whatever region we are considering till now, those are optically thin regions. So we see that the multiple scattering and single scattering, it doesn't vary much. So single scattering, it gives good results.
So you are assuming it to be single scattering?
Yes, yeah. But we try multiple scattering also. We compare the results. So the stars and the stellar spectra, for that of course we have available star catalog, Hipparchus, Gaia, anything we can use. Then for some parameters like dust number density and assumption about dust distribution, we trust the literature. Whatever best thing is available in the literature, we trust on that. Yeah, then we need the observed intensity at the dust locations. So for that, we use observations from different missions. Like till now we have used Galax, we use Voyager, and we also use UVIT data from AstroSat. And then with different combinations of AMG, we estimate the output intensity. And as I have mentioned that this till now, we are trying it for star forming region, of course, because we are just seeing the dust scattered light, so it has to be star forming region. So we started this work with Orion, and for Orion actually the results were pretty good, and there we estimated A as 0.7 and G as 0.6. This was published in MNRS. And here we have seen that the FUV light scattering is predominantly from the foreground dust that provides for at least 84% of the scattered radiation. So as I have already mentioned, there are of course some other factors, but we are not considering all those things. We are just saying how much this dust scattering can explain, what fraction of light. So similar type of work we are doing for some external galaxies like UGC 4305. So for this work actually we are using UVIT data, and this is almost done. We have not yet submitted. I've already finished. So here we have obtained some medium value like 0.2 and A equals to 0.2 and C equals to 0.3. So this is for UGC 4305, which is also called as Homburg 2. Similar kind of work we are doing for LMC also. So here you can see some model images of FUV scattering by dust. Here we are considering the 30 Doradus region in the LMC, which is active star forming region. So similar kind of work we are doing for SMC also. All the works are actually going parallelly. But all those results, because of lack of time, I am not showing here. Now, as concluding remarks, I will just say that dust scattering alone can account for the diffuse FUV background to significant extent near star forming region, and as improvement we are trying to do infrared modeling also to constrain the dust properties better. So till now we have modeled the FUV intensities. Now we are also doing it for IR. So this work we started with my first student Gautam. So after finishing his PhD, he did one postdoc from IISc Bangalore. Now he is placed in one of the colleges in Guwahati, North Guwahati College. And now this work is, Ulog is doing the work for Homburg 2 and also for LMC. And along with Ulog, we have some MSc project students from time to time. The next speaker, Vivek, actually he was also involved in this dusty work he did for SMC. And then just to introduce my students, Pranju and Rukaya, they worked on lasers with Professor Ranjit Misra from IUCAA. So after completing her PhD, Pranju joined Northwest University, South Africa for postdoc. Now she is in APC Paris for her second postdoc. Rukaya is doing her first postdoc in Northwest University, South Africa. Anshuman has just submitted, and Ulog is going to submit once we finalize the results. Ritik is continuing the work of Pranju and Rukaya. He is working on lasers. He has presented his work. He is also working with Professor Misra. Then Shwagat is trying to develop some UV catalog. He will be speaking tomorrow. Stita is the newest entry to the group, so probably she will also work on dust. So that's all from my side. Thank you very much. So it's just a view of my university.
Okay, hi everyone, good afternoon. So thank you very much for this opportunity, Vivek. So I'll be talking about the effect of quasi-normal modes on compact stars. As yesterday Dr. Gogoi and today Dr. Pamukar already gave a brief introduction, so that made my life easy. So I won't be speaking much about the introductory part. So I'll be going briefly giving about some motivation and why I studied this work. I did this work during my postdoc time. So okay, I did it with my collaborators, Beznagov, Radutsa and Pratik Thakur. So this is the outline of my presentation. So I'll be speaking about the motivation neutron stars, how GW constraints are there to constrain the neutron star equation of states, followed by the results, and finally concluding with the remarks. Okay. So to motivate, so why do we study neutron stars basically? So if you see the QCD phase diagram over there, so neutron stars basically lie on the right hand side of this. So you can see neutron stars and neutron star mergers, so which cannot be explained by any terrestrial experiments or so. Those area in QCD matter phase diagram cannot be explained in terrestrial facility. So we have to go for like astrophysical objects which are neutron stars, because in neutron stars matter is found to be there by nature itself. So studying those neutron stars, we can know about the phase diagram and that particular right hand side corner, as well as the neutron star merger scenarios. Okay. So there are certain other aspects like hyperon delta pulse results in massive neutron stars, which can also be explained via some models which we have developed. And there are another thing called the tidal deformability, from which that is another constraint from GW, which provides a very strong constraints at the intermediate mass neutron stars, from which we can know about the neutron star equation of states. Okay, so briefly, this is the anatomy of a neutron star. So it can be divided into four regions: the outer crust, inner outer core, and inner core. So pretty much up till the outer core, we know about, it's pretty much clear that there is neutrons, electrons and protons, superconducting state actually. But in the inner core, it's still an open question owing to the recent observations of massive neutron stars, whether the hyperons, like the exotic degrees of freedom, can be present or not. That is still an open question, it is still not solved. So our model, actually we developed certain aspects which actually provides hyperons as well as other exotic degrees of freedom that can be included, provided that also satisfy the neutron star observables. Okay, so so why do we actually need to include hyperons or exotic degrees of freedom in neutron stars? So basically, the whole thing boils down to something like, if the neutron Fermi energy, basically neutron star is mostly composed of neutrons. So if the neutron Fermi energy is greater than the bare mass of the hyperons or the exotic particles, so by nature, by physics, it's possible that those particles can come into the picture and can be in the ground state. Okay, so that's how. So we have found that the density is so high that the interior neutron stars, those hyperons or antikyons or those exotic particles will be present. Okay, so that's why we include this particular exotic particle spectrum. So next, let me give a brief introduction of why like neutron star mergers and astrophysical as colliders. So in GW17 we saw that two neutron stars they merge and they form a protoneutron star and then a neutron star. So here it's the first part is the inspiral phase, the second part is the merging phase, from which we get the tidal deformability constraint. But the right hand side part, that is the post merger scenario, that part from experimental point of view, actually it's still beyond the frequency. Actually because of the technological constraint, we could not, till now we have not been able to determine the actual frequency range, but with the advanced LIGO detectors also will be definitely. So my particular talk is particular based on the post merger part, where those particular part has the quasi-normal modes. From there, basically I want to so if we get a certain estimate of F mode or those oscillation mode frequency range, so I can constrain the nuclear saturation parameters or the equation of state basically. Okay, that is my main motivation of this work. So here, in presence of external and internal disturbances, compact objects may perturb producing quasi-normal modes. So okay, so these three are the motivations. So as I have already mentioned that ZW associated with F modes are most favored to be observed by first by the next generation telescope. So even before we have the F mode frequency range, so if we can have some estimates of okay this particular F mode will constrain this particular saturation parameter. So then after we get data, after we have that particular range, we can constrain it further actually. So that is what we are doing. We are doing correlation studies and how these particular F modes are correlated with the nuclear saturation parameter also. And again, one small another part is to investigate the finite temperature effect. So up till now we are talking about the cold dense matter part, but for proton-neutron stars, basically thus the Fermi temperature is much greater than the temperature of the system is much greater than the Fermi temperature, so we cannot consider those to be cold. So we have to consider certain finite temperature scenarios to actually visualize the scenario. So we are we'll be studying some effects of finite temperature. That's a small part of the work on F and P modes. Okay? So this is the model that we consider. This is the covariant density functional model that we consider over here. The equation of state from this Lagrangian, we developed the equation of state, the relation P versus the pressure versus matter pressures versus energy density, and the equation of states that we considered in this work are tabulated over here. So DDB is the one that we that our group constructed based on Bayesian approach for the cold dense matter. So here. And the others are based on, we have others for the finite temperature equation of states we have taken from a database called Compose actually. So this is based on DG2 equation of state. So this particular from HSDG2, that means the nucleon, you can see the degree of freedom DOF, those are the equation of states, those are the particle spectrum in those particular equation of states. So there are a list of particle spectrum like nucleonic, hyperionic, delta, as well as nucleonic, axionic. So we are studying a broader picture of how this particular exotic degrees of freedom may affect the quasi-normal modes also. Okay, so these are the neutron star observables, which parameters which this particular equation of states have estimated or so. So for this, so coming back again to the neutron star structure solutions from the equation of state that we have considered. So we have this particular equation of state, these particular MR relations, this temperature profiles are provided by S by A and entropy per baryon equal to 1 and charge fraction.
How much compactness will achieve with your method?
Highest compactness we have achieved is like 0.25 or so actually, right? In certain, like this is for 1.4 solar mass, so that one, okay.
So this compactness is affected by this your hybrid structure.
Exactly. So actually, this is one thing. So this compactness is for purely nucleonic case, but obviously you also true that the exotic degrees of freedom they affect the compactness. They make the star more compact, and which will in turn affect the F modes or the oscillation modes. Okay. So okay, let me quickly go through this. So the thing is that, so S by entropy per baryon equal to 1, those correspond to finite temperature scenarios. So basically the thing is that, so if you hit the star basically because of the increase in kinetic energy, the star will enlarge basically. So this black line corresponds to the one with T equal to 0 case, that is cold dense matter. But the other ones with the finite temperature equation of state are hot dense matter basically. So it's a balloon sort of. It's getting bigger in size because of the kinetic energy provided by the temperature. Okay. So right hand side you get it for the different exotic degrees of freedom. So these are the correlation plots which we have seen. So here we have taken the Cowling approximation. So we can also Cowling. So we have not considered the full GR scenario, since we want it just to see the correlations of how they are correlating, so that once we have the data, the correct thing will be to estimate the frequency modes with GR, and then calculate, but that will be for like the actual frequency modes, actual frequency range. So since we do not have the actual frequency range, we just want to see how they correlate with the nuclear saturation parameters. And the F mode, sorry, I wrote here. So F mode varies by 33%, and the P modes vary by 14% with the GR scenario, full GR scenario. So for our objective, so we did not need the full GR case for our objective of this work. So, but for actual correct, in order to be correct, so we need the full GR. So here we have seen that we are going to get two cases, like one for 1.4 solar mass star and one for 2 solar mass star, like in the mid range and the high end range. So we have seen that for different saturation parameters like K-set, Q-set, symmetry and energy parameters, they correlate up to a certain extent. And interesting thing is with that the effective mass basically. So effective. Okay, sure. Okay, I'll round it. Okay. So the main thing is the effective mass here, because effective mass, we do not have much constraints from nuclear physics experiments on effective mass. So since F modes are related to, we have seen not completely but to 50% or so, they are related, or 47%, 40.47 candle rank coefficient, they are related to M effective. So if we have the F mode frequencies, so we can definitely have a good constraint on effective mass, which is not much available, not up till now. It's not a good constraint from terrestrial experiments. Okay? So these are the correlations from frequency modes and central density of neutron stars. So here we have seen that the F modes, this particular graph, since it has a very good candle rank coefficient 0.84, so it mentions that, it explains that F mode explains the interior of, actually probes the interior of neutron stars. So F modes are very important in that particular aspect to check whether hyperons will be present or not. And the right hand side is for P modes actually. So the narrow part, that particular signifies that this particular case, this particular parameter, the correlation is somewhat EOS independent. So independent, like whatever equation of state you use, we guess this we will get the same sort of correlations. Okay, so coming to thermal composition, so we can see because F modes and radius are related, so more the radius, lesser will be the F modes frequencies or P mode frequencies. So you can see greater, since you can see here, since the radius is greater, so F modes will be lesser, and vice versa, and if radius is less, F modes frequency will rise. Okay, so same thing continues for the hyperons, as Professor Gustin already said, that with exotic degrees of freedom, you will get, since the compactness increases, so you get higher frequency modes. That is what is directly evident from this particular curve and this also. Okay? These are for two different temperature regions, temperature scenarios, but the physics remains the same. Okay, so to summarize, so it is found that the oscillation modes correlates negatively with nuclear saturation parameters, which is a good thing. Anyhow it correlates, so we can have some good, once we have the F mode frequency actual values, we can have a good estimate on the nuclear saturation, those particular values for parameters. And a correlation exists between the frequency mode of frequency F mode and central density, suggesting that F modes actually probes the inner core of neutron stars. So F and P modes are found to have different sensitivities to different domains. So F modes is more for the inner one, and P modes basically they explain well the outer regions of the stars. Okay, outer regions of the neutron star. So hot stars with exotic degrees of freedom have larger values of mu f and mu p than the nucleonic counterparts, which is directly explainable. Okay, this is attributed to the higher compactness. So as a future objective, we plan to study the impact of quark deconfinement in hybrid star scenario in context with QNMs, which will give rise to gravity modes, and also we are also looking for the full GR cases. Once we have the data, then we can give this particular full GR case is the actual correct assumption to do the actual study. So for detailed analysis, you may check our papers for this one. So, and thank you very much for your time.
Hi everyone. I am Sagar Singh Gwadi from Tezpur University. So I'm doing PhD. This is my fifth year. So my topic is asymmetric warp in these galaxies, role of gas gravity and dark matter halo. So these are the outlines of today's talk. So first I will go to why I have chosen to work this. So and then I will talk about that dynamical modeling of our problem, and then solution of that problem, and I will discuss the results. So the main motivation is like from recent observations, like a thing surveyed as Cebu and various Sloan digital sky survey. So it is confirmed that this galaxy shows disk rough, that is the disk bends above and below the mid-plane. So there are various types of disk bending like U-shape warp, S-shape warp, and L-shape warp. So these bendings are primarily asymmetric. That means the one side is longer than the other side. So these results are shown by various authors like this Sunset Sevendra, Surun, and Subramanian, latest by. So there are a few mechanisms for generation of such asymmetric warp in these galaxies. So main mechanisms includes like tidal interaction, gas inflow, and apart from that, superposition of bending wave is also influenced. So this has been shown by the Saha and Jog, which is my collaborator from IUCAA, and Pege et al. So Saha showed that superposition of bending modes or bending waves can generate various type of asymmetric warp such as U-shape warp, S-shape warp, and L-shape warp. But they have analyzed only for that single one component disk only, that is by taking only stellar disk. So I have included here the gas disk also. In other words, I have extended their work. So the inclusion of gas disks have influenced the particle distribution. It is found by the various authors. So my aim is to investigate how this self-gravity of gas may affect asymmetric warp. So for that I have considered distribution of stars as exponential, which is given by the Feynman, and for gas distribution I have taken of VGL, and for dark matter halo I have chosen the isothermal halo potential. So and then we have derived that dynamical equation of bending wave. So the particle displacement along that particle displacement of this above the midplane is given by that of equation 1. So here omega r, this represents the angular frequency of total angular frequency of this, that is which is the combination of the stars, gas, and dark matter halo. And on the right side we can see that this term, first term, is the force due to the stellar disk, and second term is the self force due to the gas disk, and third term is the force due to dark matter halo. So the solution of that equation 1 has the form of that equation 2, and that the form of that self forces are given by equation 3, 4, and 5. So after putting all this equation in equation 1, that is the dynamical equation, so we can arrange into a discrete summation form of equation 6. So where these other terms are given by this. So equation 6 again can be written as a compact form, or which we call it eigenvalue problem. So it's given by in equation 7. So here omega represents that oscillations of frequency of bending wave, and Hm represents the shape of the bending wave. So after solving that equation 7, we can get the oscillation frequency of bending wave and that shape of the bending wave. So
Yeah. Okay. Next, how to solve that quadratic eigenvalue problem. So first we have to convert into generalized eigenvalue problem, and then we have to solve that linearized eigenvalue problem. So I use that Python package called sci to solve that generalized eigenvalue problem. So as an input parameter, I have taken this value. So mass of halo is the 2 times of the mass of stellar disk, and that core radius is 3 times of that this scale length, and RG that means sorry, I have written wrongly here, so it should be R25. So it's around like the 6 times of that this scalar length, and that we have chosen that ZG at 0.1 and ZS 0.1, and that time we have normalized 1/3 of that m equal to 1 frequency. And here n represents the number of rings. So generally what we do is we divided the rings as the concentric ring. So that n represents the number of concentric rings here. So to analyze that the mass of influence of gas mass on asymmetry, so we have varied from 0.5 to that of 0.9 of mass of stellar disk, and then Q is varied from 0.7 to 0.9. It is the when we increase the value of Q here from 0 to 9, so it becomes the more oblate from oblate to spherical one. So this is the rotation curve for my input parameter. So we can get the reasoning with rotation curve for the input parameter. So after solving that eigenvalue problem, that is equation 6. So I have plotted that eigenspectrum plot, which is shown for m equal to 1 mod in equation 3. In figure 3. So we can see that all eigen modes are, that is, all the frequency are the real frequency. That means these waves are stable, they are neither growing nor decaying. So in that boundary, so where these boundaries came from, so from the dispersion relation of the wave, we can see that when there is no self-gravity, all the eigenmodes are lies in between two boundaries. That means the omega has two solutions. One is the omega minus u, and another one is omega plus u. So so these modes are not important that the which lies in this boundary, and this also boundary. So there is one point in between this boundary, what we call is a discrete mode, which is neither decaying nor growing or yeah. So I have forgot one thing to mention here.
What actually specify this part?
Yes, I come to that. So this is called gap. So this solution, these eigenmodes represent that the discrete mode which shows the shape of the disk bending. So corresponding to that eigenmode, this eigenvalue, the eigenvector represents the shape of bending. So I will show you later. So I have solved that for m equal to 1 mod. So similarly, I have found that there is this one point that represents the shape of disk bending. It's here, yeah. So from for m equal to 1 mod, so we can get that U-shape bending, and for m equal to 1, we can get the S-shape bending of these. So this is done by augmenting right and left eigenvectors. So we can measure that asymmetry by this formula, using this formula. So we indicate this right side angle through this mid plane. This is alpha r, and on left side it is alpha l. So after using this formula, we can get a 0.32 asymmetric index. So this asymmetric index lies in between 0 to 1. So when it's 1, it represents the highest asymmetry. When it's 0, it shows that there is no any asymmetry. So I have measured by making that dark matter halo by more spherical. So what I have found that that omega naught by omega ratio, this this value decreases when I increase that Q value, which means that omega naught oscillates more slowly than that of omega 1. That is, mod 0 is oscillates more slowly than that of mod 1. The asymmetry of that S-shape bending generally depends on that U-shape bending. That means the frequency of U-shape. So when the U-shape amplitude is higher, when the amplitude of mod 0 is higher, then the asymmetry arises. So here we can see that as the omega naught is decreases, that means the frequency decreases. As soon as the frequency decreases, its amplitude becomes higher. So when when two are superimposed, that asymmetry rises linearly. So I have shown this the phase map of this asymmetry. So we can get that 0.7 at value of 0.7. We can get asymmetric index of 0.22 and highest as the Q equal to 0.9. And next, I have analyzed that by increasing the gas mass. So what we have seen from that, when we increase the gas mass, so from that 0.05 to that 0.09 of that stellar mass, so we have seen that there is no mass decrease in that eigenfrequency ratio, and hence the asymmetry remains almost linear in this case. So I have shown here some case map of that Higgs displacement. So in conclusion, we have studied by asymmetric index by superimposing that m equal to m1. So that the coexistence of gas fraction in Higgs has negligible on asymmetric one. So asymmetric index is in the presence of gas is highly dependent on that halo set. So one can extend this work by including others dark matter halo, which generally discrete are very for Q in outer disk, and one can make the stellar disk truncated at around like 6 discal length, and then one can extend that discal length, gas discal length up to several times of that stellar disk. So thank you.
Hello everyone, I'm Gautam from Pune University. I'll be presenting.
Gautam College,
Yeah.
College or university?
No, we are at university now.
Yeah, I just missed.
Thank you. I'll be presenting my work on geometry of the large resonant cloud based on the multivariate analysis of multivariate civil vectors. So as my colleagues and previous speakers have already spoken on classical physics in great extent, I'll be giving a very brief introduction on those, and I'll be speaking on why CFIs are important in astronomy, then on the multiphase peer relations and the methodology and results of our study. So classical CFIs are intrinsic variable stars, and those undergo pulsation due to perturbations in their hydrostatic equilibrium. These are intermediate mass stars for which the mass range is 3 to 10 solar mass, and this luminosity is up to 10⁵ solar luminosity. These are also young population of stars, and these lines at the very narrow strip in the H diagram. The figure shows the brightest known CFID in our galaxy. These are SPPs. So this is the typical light curve of typical phase light curve of particle speeds, where 0 to 1 phase denotes the one complete particle speed. So this type of stars have very strong correlation of their luminosity with their periods, and this is known as the period luminosity relation. It was discovered by Henrietta Leavitt. The relation is like this, where beta and alpha are the slopes and intercepts of this relation, and m is the absolute magnitude of these stars. And this figure represents the period luminosity relation obtained by Wendy Friedman and collaborators in 2008. So why are these important? Is that if we can calibrate the periodization of nearby cities in our galaxy using parallax or those in the LMC using the secondary distance calibrators like decimal binaries, we can then find out the distance of faraway galaxies using the CPs in those galaxies, which also might have hosted type of supernova. In that way, we can determine the absolute magnitude of those supernovae and find out the distance to faraway supernovae, and in that way, we can determine the Hubble constant. Previously, in some work very recently, it has been found that periodization has a variation depending on the position phase of Cepheids. It has been this figure, so it is we have 0.8 slope variation with position phases. It is done by Koga and collaborators in 2022. As well as we can also see that the dispersion in periodization also varies with the position phases, and it attains a minimum at a certain phase. And we can compare this to the mean type periodization as obtained by region collaborators for NGC 4258 Cepheids. So we can see that like for the Cepheids lying in the outer part of the galaxy, NGC 4258, the standard deviation, that is the dispersion in the periodization, it is very comparable to the Veben dispersion, and it is in Ivan the dispersion is very less. So we can it can have very huge implications for the determination of Hubble constant and also some implication to the Hubble tension. In our study, we have used data from these two databases, Hubble 4 and Gaia 3. We have used about 3,300 Cepheids, which have light curves in both datasets. And our methodology is as follows: we have first collected this multiband data and phased those light curves using this phasing relation. We have done then Fourier decomposition using a Fourier trees function of a very suitable order, and this suitable order is given by this autocorrelation equation and the Burst criterion. This is the diagram of a Fourier fitted light curves of two Cepheids, one FU mode and one FO mode. And the black dots are the phase points collected for our study, and the red line is the Fourier fitted line. So from the Fourier fitted light curves, we have the multiphase magnitudes, and we combine these multiphase magnitudes with the position phases to study the multiphase periodization in the first iteration of our study. So we have a two iterative step in our methodology. So in the first study, we have done ordinary least square minimization, in which we use a very approximate equation because we do not apply any distance or any correction to the magnitudes, and we fit a model to the data to get the approximate multiphase periodizations so that we can determine the apparent distance modulus of these stars in LMC. And then what we do is the rating of it. We use Cardinal rating law. We have fixed the RV2 3.53, and we used weighted least squares innovation for this part, where weights are determined by various kind of variances present in our study. The model fitted to the data is of a similar kind, but the estimator is now different. From this, we can get distance modulus and the rating values. Like from this one, the distance modulus and the rating values we can have from this, and we can use those distance modulus and rating values to correct the multiphase magnitudes and get the corrected multiphase periodization. So the results of multiphase PL slopes is like this. So we have also considered breaks in periodizations. We have long period periodizations for long period Cepheids, and for short period Cepheids we also have. So we can see that for long period Cepheids and short period Cepheids, the trend is very opposing for the PL slope. It is also seen for the PL 0 points. And sorry, this one.
One curve is showing abnormal behavior.
No, I think it's expected. It's not abnormal.
But other
So these are actually different types of bands. So this I band. Yeah, this one is for short periods and this one is for long periods. So LMC is dominated by short period series. So overall trend is towards the
other curves means associated with okay. These
Yeah.
curves, what are these?
Diesel, all diesel.
Yes.
Yeah, these are associated with different bands. So we have I band, then P band, then Gaia Z band, and Z is yeah. So can I move on? So we have also constructed a rating map based on the rating videos we have found in the study. And these red dots actually denote the fields for which we have found negative rating values, that is physical rating values. And it is about 36 fields for which we found negative ratings. Those are dominated by very huge errors, more than 50% error on the determination. And those are very insignificant because that constitutes only 1% of the about 1% of our total sample. Moving on, we can now use the individual distance modulus of the Cepheids to determine what will be the three-dimensional distribution of the Cepheids in the LMC disk. And we use this equation for determining the distribution, and where D naught is the mean LMC distance as determined by Peterzinski, and alpha naught and delta naught are the LMC center we have taken for the study. So we fit a planar model of this type to find out what will be the inclination angle and the position angle of random nodes. So the inclination angle is basically the angle of the galaxy plane with the line of sight, and position angle is the angle between the plane of galaxy and the plane of sky plane. So we have found by using the plane field solution, using these equations, we have found that the inclination angle is about 23 degrees and position angle is about 155 degrees. Now we can use the plane field to do another things to study the underlying geometry of the LMC. We have used the plane field residuals, and we have distributed the residuals along the.
Why do you use plane field or maybe what the reason behind it? Maybe curve field also?
For disk-like LMC, for disk-like galaxies, we have plane field. But if you say for SMC, you can do ellipsoid fields or sphere fields. We can also do that. But for the case of LMC, we have it fits well, and it also gives the correct values of expected values of geometrical parameters. Okay. So now we have distributed the residuals along the maximum line of sight depth gradient. So this is given by this parameter, and these are the z minus z fit values. So, and we have been this distribution. Okay. So we have been this distribution within beans of 0.75 kiloparsec, and we have traced those beans with this blue curve. So it's not a fit; it's just a trace of this lens. So we have seen that at about 8 kiloparsec from the LMC center on the either side, it starts to deviate. So it indicates a warp kind of structure. It was also identified in recent videos. Yes, almost U-type warp. And we also actually study the density profile, stellar density profile with the LMC disk. So what we do, we take a angular region of, first we have done 9 kiloparsec, and we have been there this distribution in 0.4 kiloparsec beams and fitted a density model of this type to find out what will be the average density of the stars in the LMC disk as well as the scale of the disk. So we found average density is about 3.224 per kiloparsec cube, and scale to be about 0.94 kiloparsec. We have also done for these different annular regions. So for different annular regions, we have found that the scale height actually increases. and it increases very rapidly towards the outer side of the lens disk, and that inhibits a flare type of structure in the lens disk. So this concludes my study, and this is the group I will be working with, and thank you for your attention.
Good afternoon, everyone. I am Islam from Mizoram University. Today I'll talk about the impact of love, the tidal force on the pericenter shift of stars near the supermassive black hole at the galactic center. This presentation is based on our work done with Dr. P.C. Larepoti and Dr. Zoe Moya. Describing the ocean tides on Earth caused by the gravitational interaction due to gravitational theory. Augustus Edward Howlett originally described tidal love number in 1909. The tidal love number is named after A.H. Love. In Newtonian gravitational theory, tidal love number expressed the connection between the mass multipole moment generated by tidal force and the tidal field imposed. It also measures how much a self-gravitating object changes itself in response to gravitational potential. Several factors such as mass, radius, elasticity, and the equation of state determine the tidal love number of the stellar system. It encodes information about the degree of central condensation of the star. This means that stars with a higher polytropic index are more centrally condensed and have a lower and have a smaller response to tidal phase, which results in a small tidal love number. In this work, the significant purpose was on how the influence of the polytropic index of stars on tidal love number and how that tidal love number affects on the pericenter shift of stars near the galactic center, which is an important probe for strong field tests of gravitational theories.
That means you have taken the gas, star gas as polytropic gas. You have considered star gas as polytropic gas. Because we are talking about polytropic index, therefore gas is star made of polytropic gas.
The effect of the tidal interaction on the orbital motion is measured by the tidal love number of each companion, and we consider different polytropic index for its stellar mass. Tidal distortion effect causes a greater pericenter shift in compact orbit stars. The tidal force is differential gravitational force acting on an object caused by the gravitational pull on another object. This force is due to the gravitational interaction between two celestial bodies, causing deformation in their shapes. Pericenter shift due to the tidal distortion effect is affected by the pericenter shift of the stellar object, the mass radius of the star, and it is directly proportional to the tidal love number of the star K2. Pericenter shift of stars can be used as a probe for astronomical tests of different gravitational theories. To get a sense of how the polytropic index affect the stability of a star, using a perturbative expansion gave a great approximation of the love number, which is given by this equation, wherein is the polytropic index. And we consider the multiple moments of L equal to 2 and L equal to 2 means that is K2 and L equal to 3 means K3. From this figure, we plotted the tidal love number KL against the polytropic index of stars for multiple moment L equal to 2 and L equal to 3. The tidal radius is given by this equation, And the pericenter distance is given by this equation, where MPH is the mass of the black hole, M is mass of the star, R radius of the star, K2 is the love number, and E is the eccentricity, and RP is the pericenter distance. Pericenter shift due to tidal distortion at the pericenter is given by this equation, where P is the period at which is given by this equation, I is the inclination, and which is equal to I is equal to 90 degree, and E is also E is the eccentricity, which is the gravitational constant. From this figure, we can see that we put that pericenter shift due to.
Can you show me the sine I? We have written sine I next 100 step. This angle I is angle. I is angle.
Inclination.
Huh?
Inclination
angle, right?
Yeah. Which is equal to 90 degree.
Okay. But you can use other symbol. I think better to use other symbol, alpha or something else. I specifically use for imaginary part or something else.
Okay, thank you, sir. We took the pericenter shift due to the tidal distortion against the pericenter distance RP for low mass stars mass equal to 0.18 solar mass and 1.06 this one is 4, this 2 is 4 low mass stars, and mass equal to 12 point solar mass and 30.0 solar mass is for high mass stars. And we take polytropic index n equal to 1, 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, and 4.5 are considered for its stellar mass. This figure is for
Day-2. This 30 solar mass is a star? This star, talking about star, 30 solar mass?
Yeah.
You see, 30 solar mass star, it cannot be a star. What is
Sir, can I answer that?
Yes.
So here, the reason why they consider this starting the solar mass is that in the vicinity of Sagittarius, it's still unsure, so we are just taking the high mass. Yeah, it may be intermediate mass black hole.
Okay.
So we are just playing with the polytropic index and to see how the thing is affected with stellar mass.
But their lifetime is very short.
Yeah, it's very short. So that answer will go somewhere.
Yeah. But this is not indicates here, your plot.
This figure is similar to the previous one, but this one is for Day-3, which is multiple moment of the quarter 3.
Maybe, yeah.
This figure, this is the visualization of the precession due to tidal distortion effect of stars. And this is for semi-major, and this one is for semi-minor.
Yeah, go ahead.
This one is for polytropic index n equal to 3, 3.5, 4.0, and 4.5. And this one is the polytropic index of n equal to 1, 1.5, 2.0, and 3.5. The tidal number affecting the pericenter shift of S-stars is highly influenced by the polytropic index of the stellar system as shown in figure 1. The figure displayed a plot of tidal number K2 and K3 against their polytropic indices. The rate of the pericenter shift increases with increasing stellar mass and decreasing polytropic indices. The results are same for K2 and K3. For tidal number with multiple moment L equal to 2, we can see from figure 2 that the pericenter shift due to the tidal distortion effect gradually increase as we increase the stellar mass. Similarly, the pericenter shift varies with the polytropic indices and increase with decreasing polytropic indices. The above obtained results are more or less the same for the tidal number with multiple moment L equal to 3, that is K3, which can be seen in figure 3. We can conclude that the tidal lava pathway to heavy multiple moment electrode to yields better and higher results than KG with multiple moment electrode tree. And the pericenter shift due to the tidal distortion effect is higher at compact orbit and eventually decreases in wider orbits. Future prospect is that the estimated result can be added to any test of gravitational theories for light different star near Sagittarius star using the pericenter shift as a main probe. Here are my references. Thank you.
So hello everyone, my name is Tezpur and I am from Guwahati University. So I am presenting a work on a rotating metric in FR scalar gravity and its implications near the galactic center black hole. So as from today morning, the galactic center has already been discussed, and by now the audience is already familiar with the S stars and Sagittarius A star. So I am not going to be diving into the details of that region. But we know that this region provides a unique laboratory for testing gravity. And the strong field environment of the galactic center black hole is basically 100 times stronger than compared to our solar system. So there are certain theories of gravity that have been subjected to test near the galactic center black hole. Among them, FR gravity is one of the theories that have been subjected to test. And here, when I write that FR gravity is a serious alternative to general relativity, I know it's a bold claim, but I am going to be justifying why I am saying that kind of thing. And the FR gravity is actually studied in the context of dark matter and dark energy. And the theory has been subjected to several cosmological tests also, like in the morning it has been already discussed by Dr. Sandeep Kalita. And it has been discussed in the context of expansion history, structure formation, quasar samples, cosmic void, supernovae, galaxy clustering ratio, etc. So also the remarkable detection of pericenter shift of S2 ushered in a new era for constraining the parameters of this theory through the pericenter shift of S2. And also the imaging of M87 and Sagittarius A star through the Event Horizon telescope actually has made it possible to constrain the theories of gravity through the black hole shadow actually. So we are going to be shortly seeing how it is possible. Now as it is already mentioned by Abhijit also, FR gravity contains a scalar degree of freedom called scalarons. And through the study of pericenter shift of stellar orbits near galactic center black hole, Kalita 2018 and 2020 has given a mass range on these scalarons that are in the range 10 to the minus 22 eV to 10 to the minus 16 eV, which we will be needing in the later section of this work. Now, in FR gravity, there is an asymptotically flat Schwarzschild metric like GR, and the metric has a form which looks something like this. So if you see this exponential term, if this exponential term m psi goes to infinity, you will get the standard Schwarzschild metric. Now, there is a formalism called Newman-Jennings algorithm. So if we have a spherically symmetric solution and we use Newman-Jennings algorithm, we can actually get an axially symmetric solution. And if we are using a non-rotating black hole in presence of scalarons, and we are using Newman-Jennings algorithm, we actually obtain a rotating black hole in presence of scalarons. And the Kerr-Scalaron, we are calling this metric actually as Kerr-Scalaron metric, and the metric looks something like this. And if you see, as usual, if the mass of the scalaron becomes infinite, you actually get the standard Kerr metric. And when the A is the spin parameter actually here, so when the mass of the scalaron goes to infinity and A goes to 0, you actually get back the Schwarzschild metric. Now, since Kerr metric has an asymptotically flat limit, so we were also interested to explore the asymptotically flatness of this metric. So what we did was, for the asymptotic flatness condition, we use this condition R very greater than M, that is scale becomes very large, and it has been found that a general relation between the mass of the scalarons and the mass of the black hole has been already found out by Kalita 2020 and in the context of galactic center black hole, and also in the context of early universe by Talukdar et al. 2023. So we use these two conditions and actually see that we exactly get the asymptotic flatness condition for this metric as well. Now, using this Kerr metric, we construct a effective potential. And if you see in this potential actually, what it is signifying, the first part is the Newtonian part, second one is the Schwarzschild part, and these three terms are referring to Kerr part. But because scalarons are present in this picture, so there will be some additional corrections to the potential. And what we see is this term is actually the correction to Newtonian part. Similarly, there will be correction to Schwarzschild part as well, and there will be correction to Kerr part as well. Now, using these results, First, we come to shadow. So, using the shadow of Sagittarius A star, whose diameter, angular size of the diameter is already been measured. Sir? Yeah. Yes.
You see, if what we have shown in original class to you,
Yes, sir.
this is MC square is there.
Yes, sir.
How it becomes?
Sir, actually M is actually GM by C square, sir.
GM by C square.
Yes, sir.
Okay.
So C square, yeah. Yes, sir. That M is we are just using the notations.
Yeah.
So now the Sagittarius A star's image shadow, angular size of the shadow has already been measured by Event Horizon Telescope, and it falls within this range. And using this result, we can actually constrain any theory of gravity. And how we can do that? The RSA stands for shadow radius, and it is actually related to photon radius, that is RPH, which is given by something like this. And this Pi is actually parameter. So any modified theory of gravity will have an additional parameter, and that will be incorporated in this part. So with this, we can actually estimate DSH, and we can compare if it is falling within this range or not. So what we did after this, what we see is, we use that scalar mass range that we found earlier, and we plot for that mass range for the event horizon bound for the entire mass range, scalar mass range. So in the y-axis, you can see it is the shadow diameter, and in the x-axis, it is the scalar mass range. So if you see, for this range to this range, it is actually becoming consistent with the GR. I mean, that is, for this specific scalar mass range, it is able to produce GR-like shadow. So with this, with the shadow, we constrain the mass of these scalars from in this range, 10 to the power minus 17 eV to 10 to the power minus 16 eV. Now the thing is, the high mass scalars are capable of producing GR-like effects definitely, but in the shadow scale, we are able to rule out the low mass scalars, the 10 to the power minus 20 to minus 19 eV, because they are inconsistent here, we see. But we are interested to see if these scalars have the effect in stellar orbits or not. So, since the gravity conservation has already detected the Schwarzschild pericenter shift of S2, and this is actually an animation of S2's pericenter shift near the DC black hole. So, we constructed a pericenter shift for the Schwarzschild limit of the Kerr metric, and the pericenter shift looks something like this. And if we look carefully, only the first part, this is only GR, this is nothing but GR, but additional all these parts, these are actually the correction terms arising due to the presence of scalars. And whenever the scalar mass goes to infinity, you can directly get the GR part back. So, what we do is, we study the deviation of this pericenter shift from the standard GR part. So, what we see is that in the higher orbits, you see, like S2-like orbits and the newly discovered S4716 orbit, the deviation is not there. So, the two pericenter shifts are basically the same. But if we go to very compact orbits, we see that for one of the scalar mass range, it is actually shooting up. So this we will explore further. So we use this result, and actually gravity conservation parameterized the pericenter shift for any theory of gravity in the form of FSP into del phi SH. That is basically, this is for pericenter shift in any theory of gravity, and this is the Schwarzschild precision. So whenever FSP goes to 1, we get the GR pericenter shift. So GR pericenter shift and the other theory of gravity pericenter shift, they become similar. Now we estimate this FSP. So in S2's orbit, they measured this FSP and they found it to be in this range. And we took 3 hypothetical orbits near the DC black hole, and we found that the FSP value, they are well within this range only. So they are basically mimicking GR only. So now the thing is, this was for, because this we did for 2 mass range and they are higher mass scalars. Now what about the low mass scalars? So we did not, because we have already ruled out in the shadow scale. So in one of our earlier works, we have already found that the lower mass scalars have the capability to affect the higher orbits at longer ranges. So actually, and those effects are actually detectable by the current and upcoming telescopes. And as a result, we actually come to the result. So basically what we see is that for the higher mass scalars, FR gravity and GR, they are becoming degenerate. So that is why that time I was claiming that it is a very good alternative for GR, because at that range, how are we going to differentiate between the two theories? Because those two theories are basically acting like the same. And also, but the thing is, if we go to very compact orbits, there we saw that the pericentership, deviation in pericentership was shooting up. So as a result, we might be able to get some deviation if we are able to go very far below the potential level of the GC black hole. And actually, so what we can say is that to detect the effects of heavier scalars, we need to probe very compact orbits, that is less than 45 AU. And to detect the effects of lighter scalars, we need to probe S2-like orbits. And obviously one can say that in S2-like orbits we are not able to get any kind of effect, and in the future if we are not able to, with the current and upcoming telescopes, if we are not able to detect any kind of effects like that, we can directly rule out those scalars. But right now we are keeping an open mind, and we are just saying that we need to test GR and FR gravitational theories in these orbits very clearly and properly and we see that the metric that we generated, it is actually a novel metric derived in the context of FR gravity, and we are interested to explore further prospects of this metric in the coming future. And this work has been communicated to APG.
Okay, if there is no talk, then thanks speaker for his discussion. Okay, this is the last talk, and I thank all speakers for their wonderful talks, and I apologize for my delayed presence. Thank you all. Thank you.